Welcome everybody to the British Astronomical Association Hydrogen Line online meeting. As you know, we hold these on a monthly basis. Today is the 1st of June 2026 and it is wonderful to see so many people participating in these groups. And thank you for being here from all around the world. It's marvellous. So I'm looking forward to what we're going to talk about tonight. I know there's at least 6 people going to talk about things that they're doing, and I'm interested to hear what you've all got to say, and hopefully I'll be able to learn some lessons to help myself improve what I'm doing. A little bit later on, if there's time, I'll just mention one of the projects that I'm on, and you will see one of the rather stupid mistakes that I made today, and hopefully that'll encourage you a bit that anybody can make stupid mistakes. At least I do all the time anyway. So I know that we've got, before we started the meeting, people were saying whether they had something to talk about. I know that Conrad is a little bit under time pressure tonight. So Conrad, I'd like to give you the floor to talk about, as long as you want, to talk about your project.
Okay, thank you very much. You can hear me, correct?
Very easily.
Oh, good. All right. I am going to share my screen. I have a little PowerPoint presentation, so let's try this. Let's see. All right, and hopefully everybody can see my screen. Is that correct?
Yes, we can.
Okay, great. This was a simple modification to the Sarah scope in a box that I saw online from Alex Pettit. All right, okay. Just to introduce myself to everybody, my name's Conrad Cardano. I've got a Bachelor of Science with a major in physics. I've done visual astronomy for 55 years, and I've done visual, photographic, spectroscopic, and a lot of solar. And I got started on radio astronomy last August. This is the Sarah scope in a box that we all know and love. And this picture came from the Sarah website. Before I even used it, I realized that the parabola that you have here does not match with the length of the feed arm. So the first thing I had to do was lower this by about 100 millimeters. Just to talk about Alex Pettit's modification to reduce RFI, he took some aluminum screening and he put it around the edge, as you can see in the scope of the box. So I did the same thing. Okay, I got some aluminum screening from my local hardware store. They also had these metal strips that I was able to buy very inexpensively, and I would connect those to the frame of the scope in the box and extend them out and just attach the wire screen to it. And did it make a difference? Oh, you will see. I have before and after. This is the Milky Way on the left-hand side before I added this extra aluminum shielding. This was my first attempt with the scope in the box at doing our galaxy. On the right-hand side, this is the Milky Way after I added the aluminum shielding to it. It's not complete. Our weather hasn't been very cooperative, so I've got some areas that's missing data, and I'm hoping to get that over the next few days. And as you can see very nicely, there is a difference. And my next slide is a close-up of these 2 images. Okay, this is the before, and this is the after. And you'll notice that this image is much noisier. And this arm of our Milky Way is not as smooth as the one that you'll see over here. Again, it's just that simple wire screening, aluminium, that I added to the scope in the box, probably less than $20, to make this significant change in the image. I was very pleased with it. So the conclusion is, yes, it's worth it. It was very easy to do. After I bought the materials, it only cost me a couple hours in time to complete it. So if anybody has any questions, please ask. I'll do my best to answer them. Any questions out there?
Hi, Conrad. I might ask you if the shape of the screening has some importance or not, or is only an extension of the parabola.
The way I designed mine is that it actually was an extension of the parabola. I cut out a section of cardboard that was in the shape of the parabola of the scope in the box. And I would use that to try and shape the additional shielding so that it would fit in the shape of the original parabola. It's not high precision, but I think with the 21 centimeter line, it's very forgiving. Is that okay?
Okay, thank you. Thank you, Conrad.
You're welcome. Any others?
Real quick one. How did you attach the screening to your metal strips?
Okay, let me see. Let me try going backwards a little bit. Okay, here is the strapping that I have. And what I would do is I would drill some small holes in the strapping, and I would just attach the screening to this strapping using some very inexpensive screws and bolts and washers to it. And it worked out very well. Does that answer the question?
Yeah. Very nice.
Good. This was very easy to do, and anybody who has a Sarah scope in the box, I would certainly encourage you to do this because the results are worth it. Now, this is my optical observatory behind it, and it's interesting to note that when I'm taking data for radio astronomy, I can't use the optical telescopes because there's a motor drive in here, and there's enough interference from the motor drive to distort the signal. Are there any other questions?
Yes, I had a question. When you look at that, you might say to yourself, well, you're just increasing the aperture and therefore the gain.
Yeah, that's possible.
So my question is actually, how do you know that you're blocking RFI rather than improving the aerial?
Well, I don't. I really don't. I'm just using the suggestion that Alex Pettit suggested on adding this to reduce RFI and probably also increase the gain.
Yeah, Conrad, I could jump in here. I've had I don't have a scope in the box, but when I built my earlier version of my homemade dish, I also did the same thing where I extended the edges of my dish using aluminum window screening, very similar to what you've done here. And it's really not so much RFI from terrestrial sources, like active sources. What it's reducing is spillover from ground noise, because the ground is actually at quite a high temperature. It's at 300 kelvins, where the stuff we're looking at in the sky is in like the 10 Kelvin range, right? So,
Okay.
and so it lowers your noise floor from the ground. And I can say definitively, when I tested it on mine, which was a slightly larger system, there was a dramatic decrease in the noise floor by a couple, 3 dB at least, just from adding that extra shielding around the edges. It is true that it does effectively increase your aperture, but I think the from my results where I actually looked at individual spectra and looked at the background levels versus the peak hydrogen spectrum, you could definitely see a big difference in the background noise level when you added the extra shielding around the edges. I think some of it has to do with the fact that the parabola, if your design has a fairly long focal ratio, you tend to be more susceptible to ground spillover. And so a lot of designs, especially with smaller dishes that are mounted on, close to the ground, it's helpful to have a shorter focal ratio because it sinks your feed farther into the parabola and it naturally shields it from the ground spillover. So yeah, I think that's the biggest advantage that I saw to adding the extra shielding on the outside. So
Yeah, I thank you very much. That's really helpful. I did extend this enough all the way around so that if you're looking at it from the side, you'll see this piece of the shielding before you ever see that. It does go up that high enough. I did that deliberately. Any other questions?
I talked to Alex about this design. I must admit I haven't done it myself yet, which is remiss of me. I should have done it, but I talked to Alex about it, and he was keen to point out that you don't need to follow the parabola. In fact, the design that he has does not follow the parabola. It's actually just flat panels of this aluminium window screening, because he's not attempting to actually increase the gain of the dish itself, or increase necessarily its collecting area that goes to the focal point. He is, as Jason says, just trying to reduce the ground noise, i.e. basically the reflections of signal that's coming from space but then bounces off the ground, in your case bouncing off your optical telescope dome behind you, etc., onto the dish.
Not just reflections, but also thermal noise from the ground itself, because it is a rather hot, thermally speaking, it's a hot object, and it's generating a lot of thermal noise just because its temperature is around 300 degrees Kelvin.
Oh, yeah, there we are.
It's like looking at a giant light bulb that extends everywhere in every direction, basically.
Okay.
I mean, when I give my talk later on, I'm going to talk about an alternative, which is one of its major features is how good it is at avoiding that sort of ground noise, just as part of the design. But we'll talk about that when we get to it. I certainly think your two diagrams there are dramatically different, and I think you're really encouraging me to have a go at it.
Oh yeah, the first time I looked at it, it was, unquestionable. There was a big difference. This is just coming across much more smoother than this ever did. So this alone, it's well worth doing. And it was very simple to do, which is the best part.
Can I ask, is it possible at all for you to go on the internet now and show us examples of the things that you used for this? You say the aluminium window screening. I mean, it's not something we readily or commonly use in the UK, so.
Fly screens.
Yeah, let's see. Whoops. Let me see. Any other thing that I've done with it? It's just simple screening that
I'm just wondering how I'm going to attach it to a solid dish.
a solid dish. You know what I'll do is I will. I don't have any pictures of that, but maybe for the next time or at the next SARA meeting, I will present this again because it is kind of short, and I'll add more photographs to it showing how I did this, and maybe that'll answer your questions.
Oh, brilliant. Thank you very much for offering to do that. Excellent.
Okay, yeah. Oh no, this is fun. I'm having a great time.
Ted?
Am I right in thinking that the scope in a box feed is polarized, and so the shape of the parabolic dish is acceptable for that polarized feed? It's a dipole, I think, isn't it?
No, you're not. The issue is there's no polarization coming from the sky, but when you're doing drift scans, the resolution of these Wi-Fi dishes depends on which direction you place the long axis of the dish. So that should be east to west to fit in with the drift scan, and the dipole then should be at 90 degrees to that, orthogonal to that. So it should be going north to south.
And there's not much point extending the sides of the dish because that's not really where the reception's coming from. It's
Well, it would collect
coming
more.
from the long axis.
No. That's the resolution is
the
defined by the
long
long.
axis of
Yeah, the resolution is defined by the east-west axis. But if you extended the sides, you would, and if they're extended to fit in with the parabola, then you would collect more radio waves. I mean, so somebody correct me if I'm wrong on here. Jason, Ted, Andrew, Adrian, am I saying the correct thing here? I can see from Jason's face he wasn't listening, so he doesn't know.
No, I was definitely so it is polarized. You can definitely tell by the grid mesh on the surface of the scope in a box. It's members that are going one direction, so that shows you the polarization.
Oh, mind you, I'd forgotten that. Yes, sorry, Ted. There's something else there. Forgive me, which is that if you look at the mesh, there's like a long slit in one direction, which is sort of too long, whereas in the other direction it's shorter, and that's okay to allow this wavelength to get through. Is that correct, Jason?
Yeah. So the way I believe the polarization is in the direction of the long members, and so but extending it out to the sides will still dramatically affect how much ground noise you get because it's randomly polarized, and a dipole will still respond to cross polarized signals. It's just reduced, right? It doesn't totally, it's not zero, and so there's still a significant benefit from shielding from unwanted signal coming from the ground, even on the sides. So
I would say the actual members of the parabola itself, those wires, since the spacing on them is so short in relationship to the wavelength of the 21 centimeter line, it almost looks to the wave reflecting off of it, not quite, but approximating a solid surface. So I don't know that would the reflector itself would provide a lot of polarization, but definitely the orientation of the dipole receiver is what would mostly determine the polarization. The angle at which you place the dipole, not so much the reflecting surface. And then as far as following the parabola, even a flat mirror reflects. So you're projecting some signal back into the feed, regardless of whether you're actually a parabola or not. Obviously, a parabola is the most effective shape, but increasing the area is bound to provide some signal gain, even if you're not focusing it perfectly. Anyway, that's just sort of my view on it.
So Adrian, my suggestion that the hydrogen signal coming from the sky was not polarized preferentially in one direction, so effectively the polarization of the dish didn't matter. Is that incorrect then?
To my understanding, that would be correct. Yes, a hydrogen line does not have polarization. It's random polarized, so it's all 360.
Yeah, it's really more of a matching the feed to the to the optimal orientation for the dish design itself. I think there is some preferential. The dish design does have some preferential response to polarization in one direction versus another. It's, as Adrian said, it's not, the spacing is small enough that it's going to be a relatively good reflector in all directions. But I think there is some preferential advantage to aligning the feed in a certain direction versus another. I think a lot of the guys that have experimented with this have verified that empirically, that if you put it cross-polarized to the way the design specs tell you to put it, you will see a reduced performance.
Well, certainly with the scope in the box, since it's not a circular reflector, since it's rectangular, that would make a difference the way you angle the feed.
Definitely.
So I think that would be the main result of rotating the feed across the length of the rectangular reflector.
Yeah,
probably affect it quite a bit.
I mean, I'd say that this is a picture from actually from my observatory, and these dishes are 90 degrees incorrect because south is over here, so those should be rotated another 90 degrees. But that question I want to ask about, you've got the long gap between the members here and then the short gap, and the short gap is clearly a lot less than the wavelength of hydrogen, but the long gap perhaps is a bit slightly longer or about the same as the wavelength of hydrogen. What difference does that make?
I don't know. I don't think the lengthwise gap is really it's really any significant relevance. It's just the area of the dish.
Okay, fair enough.
Okay. So the beam profile is going to generally look narrow in the direction of the widest part of the parabola, and it's going to look wide in the direction of the narrow part. So so what you're looking at is a very wide oval-shaped patch of sky that's narrow along the long axis of the dish and wide along the short axis of the dish.
I'm reminded of experiments we did at school about 60 years ago, using a microwave transmitter which was polarized and receivers which were polarized, and passing them through, for example, meshes very similar and reflecting off meshes which are very similar in to the back of those dishes. And there's definitely a difference in, as I recollect, in the reflectivity and transmissivity. In fact, I can't see that if you have the electric vector perpendicular to the long direction of those things, there is no connection between adjacent members. So where does the electricity go? They just can't react to that, surely.
I think the wavelength, the frequency of the wavelength, the relationship between the signal that you're transmitting and then the spacing of all those elements is the crucial point. If the spacing is significantly close to the wavelength, then you're going to see an effect. But if the spacing is very, very small compared to the wavelength of the signal, then it's a slightly different aspect on the reflected signal.
I think maybe the answer to that too, the reason why it reacts at all in the perpendicular direction to the electric field vector is probably due to the fact that they're capacitively coupled. The members that are close together
you get some capacitive coupling, but I do think you would see definitely a difference in one direction versus the other. I know when I was in my undergrad studies, one of my lab classes, there was a lab we did where we made a Michelson-Morley interferometer using a gun diode in the microwave range as a source with a small horn antenna, and our beam splitter was literally an aluminum plate with vertical slits in it, or actually they were diagonal slits, I believe, and so that it would basically transmit partially or transmit the signal partially, and it would reflect the signal partially. So but in that case, I'm not sure what the geometry, I don't remember what the wavelength was, so I'm not sure how the geometry of the slits corresponds to the size of the waves that we were dealing with. I think it was probably in the order of a quarter wavelength or something like that, which would kind of make sense, I guess. But
Thank you. Conrad, you wanted to speak?
Yes. Unfortunately, I have to leave. I can't stay for the whole meeting because I have guests here. But there's a lot of great comments here, so I'm going to review this whole video again. So thank all of you for your comments. They're really great. And Ted, thank you for Ezra. Without it, I couldn't do this. So cheers to everyone, and I'll see you again at the next meeting.
Yeah, well, thanks, Conrad, for the first chat. I mean, if that's going to be the 5 minutes, I don't think what the rest of the evening is going to be like. And I'm feeling that it's a good job that Eduard pulled out, so that we got some space for everything else. Thank you, everybody, for all your comments. Okay, next on our list we have John Savage. John, if I can give you the floor.
Hello, everyone. Okay, can everyone hear me, first of all?
We can hear you very well.
Excellent. Okay, I'm just going to try and share my screen. This is the first time I've tried this on Zoom, so here we go.
Yeah, I can see your screen well.
Okay,
H-Line astronomy at
H-Line
Roche
astronomy,
Farm.
it's very nice noctilucent clouds.
Before you move forward, where is Roche Farm?
In North Dorset.
All right, okay.
The United Kingdom.
Yeah,
okay.
Thank you.
Right, I've come down with a terrible cold, so if I cough and splutter, please excuse me. Okay, let's press on. Okay, so this is... oh, crikey. I can't move the slide. Oh, there we can. Okay.
Yeah.
First of all, a bit about me.
Just to say, take your time. There's no rush. Take your time.
Well, I think people want to get to bed sometime. This is quite long, actually. Okay, I had a 45-year career in geophysics, mainly for oil and gas exploration, and much of it living abroad. I've had some interest in astronomy since childhood. But obviously, our involvement waxes and wanes due to all the sorts of other things that go on in the lives of people like us. I've been much more active in astronomy since easing into retirement from about 2011. And I did a lot of visual at first, but I've more or less abandoned that. Eyesight and climate change, the sky conditions here in the UK have got a lot worse in the last 10 or 15 years. And the guy down the road has started to use an unbelievably bright light every night. Okay. Currently, I do a range of things. I do exoplanet transits for the Exoclock project. I like to go to eclipses, so I'm off to Spain in August to do that. I do all sorts of sky monitoring. I've got an all-sky camera and a TAPO cluster. I'll show you pictures of those. I also monitor meteors. I've got 4 meteor cameras at the moment, feeding the GMN and UKMON organisations, and 2 radio meteor systems. So I've now accumulated a bit of experience with software-defined radios for that. Got a passing interest in particle physics and run a Pico muon detector. And I suppose I've always had some interest in radio astronomy. Anyway, this is my real introduction to radio astronomy, looking for H-line signals. So this is actually in my previous house. I've got an observatory, and as you can see, it's a bit like the TARDIS. And when we relocated to North Dorset, this is where I set it up. And when we moved in, we had wonderful dark skies, but they have got worse in the last 10 years that we've been here, for sure, which is a great shame. And if you look, can people see my cursor? Can people see my cursor?
Yes, we can see your cursor.
Okay.
Over the Yagi there.
I can increase, yes, that's my Yagi, that's my H-line Yagi antenna. So, this is some of the other equipment I have.
Sorry, that H-line antenna, is that one you built yourself or one of Alex's?
It's Alex's design,
okay,
but my build.
Okay.
And I'm going to talk about that a little bit. And this is some of the other stuff. So I've got an all-sky camera which does a good job of picking up aurora and all sorts of interesting things, actually. And this is a TOPO cluster, so these are just ordinary security cameras. Well, they're not just ordinary, actually. They're a particular model which works well in night sky conditions. And then here, left and right, I've got 2 of my 4 UK Mod video cameras, so these monitor meteors. And the data goes into the UK Mod database, and you can have a look at all the amazing amount of meteors that they collect and solve the trajectories for. Okay, so I'm going to talk about my H-line experience so far. Actually, Andy has scheduled me for a meeting in September. So I started to put this presentation again a few weeks ago, and I've been adding to it ever since. I reckon I'm still a beginner, but I'm learning fast. And I'm going to be talking about the antenna I use, something about antenna characteristics, the acquisition software that I'm using with it, and I've got a slide on wretched windows and the sorts of things that I have experienced with it. Then going on to some parameter setting experiments. I'm going to talk a little bit about what we see on easy call screens. A little bit about processing software, and then now I've got a single slide, my future with H-Line and other radio astronomy projects. So at this stage I do want to thank Andy and Ted and Alex for making all the material available, particularly videos. Looking through those, I've learnt a lot because I didn't attend the first couple of meetings for this group. So let's go on. Well, I was looking through various things, and my heart went out to the Yagi design. I have to say, I just like the look of it. So I have built a Yagi antenna from Alex Pettit's 15-element design using circular elements. Same dimensions, but metric fasteners and the aluminium discs are slightly different metric thicknesses, and I don't think that makes a heap of difference at all. Alex's design was quite a lot of wood, actually, but I tend to use 3D printed parts because I just find it a much easier way of making things. I'm also going to show you disc filing jigs for getting the circular elements to good accuracy too. The antenna still has a wooden dowel down the axis, and it's nominally 9mm. Actually, it's a little bit bigger, which is good because M10 nuts grab onto it quite tightly, and that's one of the things that you really need with this design to keep it together. So, just like Alex says, he draw out the discs roughly, snip them out with one of these aviation tin cutters, drill a hole in the middle, and then what I do to get the diameter exactly right is I use these jigs. So these are 3D printed jigs. There's a post in the middle, and that goes through the hole on a roughly cut disc, This goes over the top, and then it goes into a vise, and you turn it round, and you just file the aluminium down until it meets the 3D printed jig, and that way you get a good circular disc out of it. So my completed installation looks like this now. So there's the Yagi. I've used 3D printed spacers instead of the water pipe that Alex recommends. I've mounted it on until about a couple of years ago, when we got fibre broadband. I was connected to the internet through a microwave dish, which pointed at an antenna about 4 miles away and got me my internet. But that became redundant, as did the PoE Ethernet cable from this point into the house. So I thought I would reuse that, and it all works very well, actually. So here we've got the antenna. There's the back end of the antenna, and I'll show you a close-up of that a little bit later on. I decided to put a pole on here and a counterweight to keep the thing reasonably well balanced, so that it wouldn't jog around and achieve another altitude on its own. And then nearby I've got this weatherproof connection box, 10 quid from Amazon. So this is a bit of a close-up. So here's I think this is the reflector, and this is the patch antenna. I think that's the nomenclature. And it's exactly the same design as Alex describes in his work, and it goes straight into a Sawbird LNA filter here, an H-Line one. I decided to put this dial on, and I think that it's accurate to within a couple or 3 degrees, something like that. So it gives you the altitude. I've called it SALT, because I've also tried to align it as accurately as possible with the south azimuth, so that it's the southern altitude. And I decided to call that because, in principle, you could go beyond 90. Altitude is normally 0 to 90, but if you go up here, then basically you've gone past the zenith. I also 3D printed a weather shield, and that gets taped onto this member here. So there's the back end of it, and this is what it looks like in the early morning, when there's still dew on the director elements. Oh, I think I've gone the wrong way. Yeah, there we go. And this is a front-end view, so you're looking at the Yagi antenna here. There's the wooden dial with an M10 nut on it, and there's a white spacer there too. This is the altitude dial. This is the bracket that held the microwave dish, and it's easy to print a 3D thing which fitted snugly into the slots either side. It's held together with M6 threaded rod, so that it's nice and snug. And on this side I have an altitude clamp, so that's a bit like a dog clutch really. There's a disc with spokes in it, and then when you either loosen it or tighten it, and a corresponding dog clutch thing grabs that and holds it quite steady. So I'm pleased with that. Oh, this is looking inside the box. So I've got a mini PC which was repurposed from something else that I did a while ago, and a PoE splitter. So that provides power to the computer, and then from the computer to the RTL SDR, and from the RTL SDR to the Sawbird, and so on. So this is the input Ethernet cable from the house. This is the power to the computer, and this is the RTL SDR, and this is the LMR 240 cable to the antenna back. So not much in there really. I think there's room for a second piece of equipment if I decided that I wanted to do that. So this is one of Alex's diagrams, and of course I was looking these a lot to try and get the dimensions and try and make it properly. And I noticed these things. VNA required to adjust the impedance or the resonant frequency. And I didn't know this, but you adjust for one at one end and the other at the other end, which I found quite amusing. Anyway, I had no idea what a VNA was. So I decided to educate myself and obviously went online to find out what they are, Virtual Network Analyzer. And who doesn't know what a VNA is? I think I'm probably well behind the curve. Yeah, you all do you? Okay, well anyway, it measures the complex impedance and it's great for evaluating antennas. So I got a light VNA. It's not the cheapest, but it goes up to 6.3 gigahertz. And the reason for going for a slightly more expensive unit is because I have quite a lot of other antennae. I do a certain amount of radio control, and I wanted to be able to go into the gigahertz range to have a look at the antennae that I have for that. Anyway, so I connected it up to the Yagi as first built and got a lot of information. I found that the resonant frequency was 1390 megahertz, which is actually 2.1% lower than the 1420 megahertz that it's supposed to be designed for. The impedance at the resonant frequency is 41 ohms, and the maximum return loss was 20.82 dBs. And a 1420, you've got an impedance of 23 ohms, something like that. And I have to say, I thought, well, that's not too bad. I mean, it's within a couple of percent for something that's, I suppose, a bit rough and ready and not, micrometer accuracy. But anyway, I decided that I wanted to try and get the resonant frequency a bit better and thought that if I closed up the gap between the back two elements, that would probably do it. So all I did was actually to tighten the spacer screws. There's 3 spacers between those elements. So I just tightened them up. And that changed the resonant frequency to 1414 megahertz, which is 0.5% lower than 1420. And puts the impedance very much in the right range, I think, at least 55.8 ohms, and improves the return loss, and the tuning notch was visibly narrower too, as I recollect. Anyway, my thought is that that's excellent, so I was really pleased with that. And so let's go on to acquiring data. Basically, looking at Andy's video of previous meeting, there seemed to be the 2 options, SDR sharp plus IF average, and I did look at that first and played around with it for a bit. But I wasn't especially impressed, really, and I can't remember all the reasons that I didn't really like it. I think recording data was some kind of issue. I don't think that much information goes into the files in that method, and I didn't really understand some of the configuration either. Just yesterday, or perhaps it was the day before, I tried it again and gave up pretty quickly. It just didn't work, and I have a suspicion when you get SDR sharp, you get an RTL SDR.DLL, and as Ted knows, one of the things that I found when getting all this stuff together is that there are at least 3 versions of the RTL SDR DLL, and I discovered that for his software at least it was the largest one, the one with the largest file size, which worked. Anyway, I got EasyCall working, and it's been working well for me most of the time. The problems I have had been mostly with Windows. Anyway, so I've been using EasyCall.py, actually my own version of that, and I'll come on to that in a minute. And what I'm going to do is to talk a little bit about Windows issues and then go on to parameter setting. But before I do that, well, I told you that I tried the SDR sharp method, and before I did it, I was getting on easy call images like this, which is I'm very used to now, so I think that's correct. And then I tested my RTL SDR on SDR sharp, and afterwards I got this response. And I've seen this kind of response before, and I just put it down to being a faulty unit, and that particular faulty unit I returned to Amazon as faulty. Now, I'm puzzled as to why just using another piece of software should change the response so very profoundly. This is rubbish, basically. The left-hand response is rubbish. Has anyone got any idea what's going on there? Does RTL SDR store something and inside it? Can't see why it should do. Anyway, all right. So there's that, and then I, as Ted knows, I had a lot of Windows issues too. Continual crashes initially, and I had a lot of time spent with Windows diagnostics, particularly the what they call it, the system event viewer. And
John,
yeah,
can you go back to the previous slide?
yes, yeah, there you go.
Well, the one on the left is centered at 1423.5, and the one on the right is 1420.5. Is that not your difference?
No, it isn't. This is a reference one, and this is the signal one, actually. And it is coming through a different RTL SDR because I had to swap it out in order to get, restored to something that I'm used to. But signal or reference, I call it signal, I think Ted likes to call it antenna. Signal or reference, the overall shape is very similar, and I'll come on and I'll show you that some of these spikes move around when you go from one frequency to another, as you would expect. Anyway, this is consistent from record to record to record to record. You can get 100 records and they look roughly the same. This varies from one record to another, so the next record would look quite different with peaks in a different place and so on. So this is quite hopeless.
To me that looks like a catastrophic hardware failure.
Well, then that's my second RTL SDR unit that has failed, and whereas the other one arrived dead, it was dead on arrival, this one I have been working, the ID1, that's the ID that I put on it, has been working without trouble a lot for perhaps a month or two, something like that.
How can you determine that it failed? What other tests did you run on the RTL SDR? For example, RTLs are quite wide spectrum, right? So could you just tune it down to say an FM station and see if you could pick up an FM station on it? I mean, that would kind of clarify whether that really was catastrophic or just
okay. This
something
is
else.
Yeah, indeed, and I have been thinking about that. I will try that before, but it doesn't work for what I want to use it for. And I don't know.
It might not work because like you said, you're using SDR sharp, and it might just be the whole thing, just software. I mean, maybe the processing is incorrect, and I still don't understand why you're tuning to 1423. Why not look at exactly the frequency you're interested in, 1420?
Well, that's a good question. I think that I inherited these frequencies actually as defaults and easy call.
Yeah, Adrian, the higher frequency is used as an easy way to do a background correction.
Oh, okay, all right.
And it looks like he just happened to select that one randomly for one and the other. So
I see. Oh, just to look at the spectrum shape. Okay, I see. Yeah. But yeah, I mean, why not just don't even use SDR sharp, or use SDR sharp and then just tune down to a regular broadcast station and see if you pick it up. That would tell you at least.
I guess the question I would ask is, what was your integration time on the two pieces of software? Were they the same as each other?
For these two plots, the acquisition parameters in EasyCol are identical.
Sorry, the one on the left wasn't EasyCol, was it? Isn't that SDR Shop?
No, it isn't. No, it's not an SDR Sharp display.
Oh, sorry, forgive me. I misunderstood you.
This is text program. This is when I took it out of SDR Sharp mode and put it back into EasyCol mode.
Oh, right.
And suddenly I found that it was not behaving as it had before I did the SDR Sharp. And this is all in a period of just, I don't know, half an hour or so.
Weird.
No, not very good. And I think it's a bit peculiar that I should have two of these units go wrong in much the same kind of way.
I have half a dozen of the things, and to be honest, they all work. So I'm quite surprised.
Aren't they quite sensitive to overvoltage?
Well, overvoltage where?
The 5-volt feed.
Well, that comes from the computer, and I presume that's...
But there's some warning about... I think they like to be under 5 volts somehow.
Well, it's a USB interface, and that's 5 volts.
Yeah.
Isn't it?
Yeah, but
I can't believe that SDR Sharp would suddenly have increased the voltage going down the USB cable to the SDR.
What I don't understand is when you showed us your box outside, you said that you were using a PoE, and so
yes.
Where does the power supply to the PoE come from?
Well, inside the house, it goes down.
So what is that voltage?
48 volts, but that's converted down to 12 volts for the computer. So that goes into the computer, and the computer feeds power to the RTL SDR. And that should be 5 volts, irrespective of what it's, what the voltage is that it's getting down from the PoE splitter.
Okay, all right.
And I have monitored that when I was having trouble with it.
I've had some various hardware issues with a couple of different RTL SDRs as well. I have actually I ended up switching to the AirSpy Mini, which is quite a little bit, about double the price, maybe a little more than double the price, but for that extra money you get a 12-bit resolution and 6 megahertz of bandwidth, which makes a huge difference, and the passband is a lot flatter. But that being said, I have personally experienced hardware issues with the RTL SDR type as well. It seems to be kind of like rolling dice sometimes, and I think it may be too that there's some that are marketed as being legit and they're actually clones and they're not as good, or so it's possible that you just got a hold of a bad one.
But yes, except that the one that went faulty when I was trying SDR Sharp had been working very well for a long period. Anyway, never mind. I think we should continue on. I sort of slightly put it down as to one of those things. Well, I just got a page on Windows issues. Continual crashes, really, when I first started. I tried a range of things, monitoring CPU temperature and computer power monitoring. The voltage that went into the computer, that was very steady at 12 volts. I disabled update, or I tried to disable updates. What I've learnt in this exercise is that Windows won't let you do that. It tells you that you've disabled it, and then when your back is turned, it re-enables it. And I find that utterly disgusting, actually.
Sorry to interrupt again. There is a little app you can download called Windows Update Blocker, currently version 1.8, and it's absolutely brilliant because there's several different ways that Windows, if you really want to stop updates on Windows, there's several settings that have to be changed. And Windows Update Blocker, which is completely free, works incredibly well, will switch them all off and give you a nice little screen window, and you can press on, press off, and it gives you a nice little icon to show you that it's off and it's on, and just really easy.
Wonderful. Okay, thanks very much, Andy. That's most helpful. Okay, I wondered whether there were some issues from the previous life of this computer, so I did a clean install of latest versions. And then I found that the .bat files, running them with a click was disabled. Managed to get that around that with advice from the internet. And another thing which I found so unbelievably irritating is that the modern Notepad, this program that's been around for decades and decades and decades, you can be editing something and then you dismiss the program, so you think you've saved your edits, and you reopen the file with Notepad and there are the edits that you've made, so you think you've saved the edited version. Not a bit of it. You actually have to dismiss it at the tab. It allows you to have several editing sessions open at once. Anyway, never mind. So I also eventually twigged that the computer was going into sleep and hibernate modes. I'm sure I switched them off originally, but with the clean installs that got reset. That's numpty me. That was stupid, really, because I know very well that those have to be off if you want Windows computer to do monitoring. And then I got further crashes and discovered the Windows Update service had been restarted, which is actually lying to you. When it says that you've disabled it, it's lying to you because you haven't really. Never mind, that's modern Windows for you. Anyway, so I did quite a lot of work on parameter setting. I wanted to see what the different parameters did, and I'm going to take you through that in a minute. But while I was doing that, I felt that I really wanted to have better access to the parameters that were being used in EasyCall.py. So I've took a copy of the program, and as Ted knows, I've been modifying it, not in any profound way, really. So this is the version that I'm currently running. It's JS5, and that's the date. But what I've done is to display on the screen a few extra things like Easy Call Gain. Now, my version of this program, you can specify the gain that you want with that parameter, but what it reports back is it should be the SDR gain, the gain that it extracts from the SDR. But that always comes out as 0, so it's not a very useful figure to have there. And then I thought, let's document the antenna that I'm using, the SDR that I'm using, and the LNA filter that I'm using. So those are put in as extra parameters into my version of the program, and they get reported here, and then they also find their way to the output files. So here they are here, Easy Call Gain. We've got a couple of defined parameters which I discovered weren't actually defined in the program, so I've made myself a note about that. Which antenna am I using? Well, I'm calling the current one Yagi 1 in case I make another one. And then and this is the ID. This is the identification of the particular SDR that I'm using. So that's the type and the ID. And then the LNA there as well. I think it's useful to document this in the output file, so if you come back later, you can see what you've done. Okay, so parameter setting experiments. The first one that I played around with was gain. Kept 256 frequency samples and 200,000 integration numbers. And at low gain, this is 0 gain, medium gain and high gain, you get these different displays. So quite clearly the floor level goes down, presumably because it's just not registering the noise with the same gain as you have up here. Not much to be said about this, really. There's no reason for not using the maximum gain, I don't think, so that's what I use all the time now. Okay, integration quantity. So I think some people at least are using 200,000. This being effectively the binning number. Oh dear. The binning number. The more you bin, the smoother is the signal. Obviously, because you're averaging over more records, and the noise the random noise that is, tends to decrease. So this is with only 10,000, and as you can see, it's quite noisy. Now, as I said, I've spent 45 years doing seismic work, and the seismic industry has discovered that the more you sample, you can't oversample really. The more you sample, the better off you are. You can always apply smoothing after the event once you acquired the data and get back from say 10,000 integration quantity up to 200,000 by adding 20 of these together to get one of those. But software binning is preferable because it allows for more sophisticated noise suppression. If you get the odd spike, you can deal with it on just one record rather than, say, the 200,000 that you might have with this arrangement. So I'm a strong believer in keeping the integration quantity down. Actually, I've settled on 50,000 because you don't want your files to be too large either. So it's a bit of a compromise, really. Okay, another one is the bin bits. This is specified by these easy coal-free bin quantity bits. So I changed that from 8 bits on the left-hand side through 9 bits through 10 bits. And what happens is that you divide the same spectral range into more samples. So instead of using just 256 samples to cover that, in this case you're using 1,024. And again, for the same reason, I think that it's good to increase the number of samples per record. In fact, I'm currently running with 4,096 samples per record, so that's 12 for the number of bits. More samples, better resolution. The spikes do have larger amplitude, but it should be easy to eliminate. I say should because actually I've run into a little bit of problem with that. But I have got a solution, not the most elegant one at the moment. So there we go. And you will see that we've got some noise spikes. And recently they've got worse and worse and worse. And I'm at a bit of a loss to know where they come from. I suppose it's RFI of some sort. Anyway, so where do the spikes come from? Are they instrumental or are they external? Well, for signal and reference, one way of detecting that is to use a reference with a center frequency just 100 kilohertz different from the signal center frequency. So this is what I have now. The reference frequency is only 100 kilohertz higher. And you can see the same pattern of some spike. First of all, the central spike, the DC spike, is in exactly the same position on the plot. But the other spikes move with the shift in frequencies. Same pattern, but a shift. And that becomes more obvious when you line it up by absolute frequency. So this spike, this is signal, reference, and you can see the spike occurs at the same position there. This C spike plus a little bit of noise on the low frequency side is also in the same place, and these spikes also in the same place. The central spike, of course, gets displaced. And that tells us something, actually. The background shape shifts as expected. So the background shape, by which I mean this 3 peaked background there, must be something to do with the instrumentation. The central peak shifts as expected. It's always in the middle of the plot, so that's also instrumental. But the other spikes are static with absolute frequency, so they must come from outside somewhere. And another thing that I looked at is the bandwidth. I tried using various bandwidth values. I couldn't get anything about it to work above 2.4 megahertz, which is the default. When you decrease the bandwidth, obviously you're looking at a smaller part of the spectrum, The overall shape is much the same, but when you get a noise spike, it is more widely separated for the lower bandwidth. And bandwidth translates directly to sample rate, so 2.4 megahertz is 2,400,000 samples per second. I wondered whether the bandwidth is limited by the A to D conversion rate. I guess it's a limitation of the RTL SDR. Anyway, I'm keeping bandwidth at 2.4 megahertz, so capture the hydrogen line signal in the flattish part of the spectrum, by which I mean this bit here in the central. Certainly want to avoid it going into the roll-offs at either end. Sorry, excuse me. This central spike worried me. I know that it's DC, and again, building on my experience as a seismologist, seismic signals don't have a 0 hertz. So whenever I saw this on this seismic spectrum, I said that needs to go. And usually the way to do that is to subtract the DC level off the time series. So obviously I went into EasyCol and played around with NumPy and managed to do that. Anybody like to guess what the output looks like? No? Any takers? Well, it looks like this. Okay. And I looked at that and immediately I saw it. I said, well, you're a stupid fool. Obviously that's what's going to happen. But, okay, but here are my further thoughts on it. Okay, I felt rather stupid that I'd even tried this, really. Obviously, if you make the mean zero, the Fourier transform will have 0 energy at 0 hertz. Exactly this point here. And I've told you why I tried this. It's habit, really. Anyway, on reflection, I thought this wasn't such a bad thing to do. It supports the theory that the central spike is due to a DC problem somewhere in the software-defined radio.
No, that's an inherent property of the RTL SDR, because it's a non-frequency converting. So what you're actually seeing is you have a local oscillator that beats with the input signal, and then that gives you the range that you can see. And when you go to 0, you're basically looking at the local oscillator signal of the RTL SDR. So the solution for that is to get a different type of SDR that does a frequency conversion to an intermediate frequency. And if I'm not mistaken, and Jason, you might verify that, doesn't the AirSpy not have a DC spike?
That's correct. I believe
too,
some RTL SDR versions I somehow are able to mitigate that spike
because they use heterodyning and they go to an IF frequency. So you're shifting that away from a 0
But
beat.
another thing, even on the ones that heterodyne, you can have issues with that, but it's usually because the I and Q are not balanced properly.
Well, that's a different issue. But in terms of the DC spike, that's because you're looking at the local oscillator at 0 frequency.
Yeah,
so
exactly.
That's inherent to the RTL SDR. You can't get rid of that. That's just what RTL SDRs that do not generate an intermediate frequency will do.
It can be pretty easy to remove in post-processing because of the fact that it's such a narrow. It's literally a single frequency bin, so you can just basically average the two on either side of it and get rid of it. But
right,
that's
what I'm saying. But in terms of the hardware, you can't. It's not a fault. It's just inherent part of it. You can't get rid of it at the hardware site. But yeah, the answer is post-processing. Anyway, I just thought I'd point it out.
Yeah, fair enough. Thank you very much. Okay, so this was my first encounter with NumPy. Okay, so we've explained, I think everyone knew what the central spike was. But what about the overall shape? I come from a signal processing background, so this sort of stuff is quite important to me, actually. Well, you can see that this is basically a cyclic signal. In other words, if you take this and copy it and transpose it here, you'll get continuity at this point. And all digital Fourier transforms on finite samples are cyclic in this way. and it's a phenomenon called aliasing, or it's another aspect of aliasing. You've got quite strong attenuation at each end, and I've said that must be due to an anti-alias low-pass filter. And its number is strong, and this doesn't come down to zero, and I'm guessing that it's analog. But somewhere along the line, you have to have an analog filter for anti-aliasing. You can't anti-alias unless you convert from one sample period to another. Then you might use a digital one. And it's not completely flat in the passband either. Also, the side lobes are not symmetric. And to my signal processing, that tells me that you are, the FFT must be seeing a complex signal, because FFTs, or Fourier transforms on real data, are symmetric about zero frequency. And SDRs do put out an in-phase and quadrature signals I and Q. So the FFT must be working on a complex signal. I guess this is common knowledge. Okay, so what about the overall shape of the spectrum? So why are there three humps like this, and this in the background? So a few factors occur to me. Perhaps it was the antenna response. I have, just to get an idea of how narrow the notch in my antenna's response is compared with the bandwidth, I've overlaid it. So these are both 2.4 megahertz from side to side, but the central frequency of the antenna is not here. It's way over to the left-hand side. So we're operating really in this side of the antenna, in fact, off the picture. Wouldn't we see a profound change in shape between reference and signal? Possibly not, as we're operating well outside the resonant frequency. Might account for low base symmetry. And I have it in mind to test this possibility by putting the reference frequency on 14 megahertz and seeing what the response looks like. Anyway, I don't think it's the antenna response. I don't think it's the LNA filter for much the same sort of reason. Looking it up, it seems that the passband for this hydrogen line filter is 65 to 70 megahertz, 3 dB points, which is 30 times the bandwidth. It doesn't say in the specs or anything that I could find about in-band ripple. I suppose there must be some variation in gain in the central part, but it doesn't seem to be important. So my feeling is that it's to do with the anti-alias, the analog filter, which really tries to cut off the frequencies which would otherwise alias. Now, I'm used to Butterworth filters, which have a flat, low pass response. So with those sorts of filters, you would expect a flat response here. But I wouldn't be surprised if it's some other design to keep things simple, really, and to also make the frequency switchable. The cutoff frequency needs to be able to switch with the frequencies that you're looking at. So that's quite a complicated thing to organize for an analog circuit. Anyway, I think this is really due to the internal filtering in the SDR. So this is my diagram. Sorry, excuse me. I have seen a decent SDR block diagram on the internet, and from memory, I've reproduced it here. So this is my understanding of how the SDR works. Basically, you go in and you've got an amplifier here, and the signal is divided to two mixers, which use the same local oscillator, but one has the direct feed and the other one has a 90 degrees phase shift. I've also seen the figure of 270 degrees phase shift, which is more or less the same thing. And then each of those goes into its own anti-alias filter, so it cuts off the high frequencies energy to prevent aliasing, and then it goes into two separate A to D converters. And the 90 degrees phase shift is called the quadrature signal, and the other one is called the in-phase signal, so it's I and Q. Those are terminology which you see quite a lot. And I think that that explains what I've been seeing, really. So it's the anti-alias filters here and here that give us the shape. So here's my summary of what I call now my current production parameters. So the gain is maximum, the bandwidth is 2.4 megahertz. I use 50,000 for my integration number, and I'm currently recording 4096, though I might knock that back to 10 bits if I get fed up with the very large, well, the rather slow to process files that I have. I actually run EasyCol using basically the command line arguments in this kind of way. So this is my BAT file with continuation, Windows continuation signal, parrots all the way down. And I like this way of running programs because I only have one file to look at. Okay, so it's working. What do I get? Well, I put the very last full 24 hours of data through EasyCon, Ted's program EasyCon, and I get 100 and something files when I do that, and I look through them, and so these are very similar. I think the only difference, if you'll be able to tell me, Ted, this is EasyCon 067 and RB. So these are ratio plots. So this is the ratio of the signal divided by the reference. And if you look closely, you can see a slight increase in signal here and here. And that is my H-line signal. I also get this lower amplitude ribbon. And I have seen that frequently. I think it's 24 hours. It's not the sun or anything. And I don't know what it is. Has anyone got a clue what this might be? All right.
It might be gain changes in your overall system due to the temperature fluctuating over the cycle of a day, because it does affect the gain response of your system.
I know that the sawbirds gains are temperature dependent, and I do see energy changing throughout the day. But you say switching gains. Why would it switch again?
We see gain variance during the day. That's true. But what you're seeing here, it's hard to see through the online call here, but we see a faint blue arc, and that's almost like there's a bunch of RFI that just is influenced by the temperature, and so you're getting a daily pattern out of it, though. It could be that it's changing its local oscillator frequency and just wandering into your world and then back out.
Yes, that's what I thought too. Actually, that's my current explanation for it. Okay.
The difference between the two plots, you want to do that?
Yeah, tell us. Yeah.
These are using reference samples, and so the name has an R in it. That's what the ANT-R is about. And then it's actually a two-step process, and I happen to just give you the results of the A, the first step. I think it kind of represents the RFI noise that it is trying to remove. And then you finally get to the second step, so the second letter, B, is the one that really matters. Two-step process. The earlier calculation didn't use reference samples, and I call it ANT-B just for baseline. You're kind of taking out the average of the noise across the whole spectrum. And so that's one of these steps at the end, I think it is. Well, it's been like 8 years now since I did this. And so ANT-RA, I can't really figure out a good use for it, but I thought it was interesting, so I put it in. It may represent the RFI noise we are removing, but I concentrate on the ANT-RB reference and simply the second step.
Yeah, fair enough. And in fact, the right-hand signal has this curtain. So there are trace-to-trace variations. I call them traces because that's seismic speak. Variations. Anyway, let me show you this. This is my processing of the same data. So, with a program that I knocked up over the last month or so, called Easy Cold QC, because the initial aim was really just to QC the data and see what it looked like. But I've
quality control, yeah.
Quality control, yeah. But I've added some processing, and when you choose your parameters correctly, this is what you get. So this is our H-line signal here and coming down here, and then you can see that ribbon also quite clearly.
And so that ribbon just looks like RFI intruder.
Yeah, okay, yeah. And I think that's what it has to be. I'm not familiar with what other people operate in this kind of frequency band, or why it should vary in frequency so much. But never mind, it's there, and you can see it for what it is, really.
We often call them like whistlers. Things just kind of come and go, and they change frequency so it sounds like someone whistling. I do want you to explain those vertical blue lines that wiggle, of all things. Go ahead.
All right, then. Then we're heading for a demonstration of this program, I think. Has everyone got enough time to do that? Okay. Anyway, just before
Can I make a comment about your potential RFI problem?
Yeah, sure.
I'm not too familiar with, again, back to my earlier question about the PoE power. Not too familiar with that system. But you're saying that the 48 volts gets converted down to 12.
Yes.
And so what kind of unit does that?
It's the PoE splitter that I'll zoom back and these are. Here we go. It's this unit here. So that takes in an Ethernet cable which also carries 48 volts. And out of that, you get an Ethernet connection, which goes into the computer, and also a 12 volt. It down converts.
I see a problem right there, and that is, I would bet probably, mostly, that somehow that converter utilizes a type of switching in order to convert the 12 volts, the 48 volts down to 12. And that is sitting right on top of your RTL SDR. Now, switching power supplies are notorious for feeding through some of that switching frequency through they're generated, number one, and feeding through some of that into its output. It does get filtered, but there's still residual switching noise that goes into the power output. That might not be a problem because of the filtering, but you're sitting right on top of that oscillator that generates that switching frequency. And it's not, that's not a required fixed frequency like you would have for like a radio transmitter or something. It's just kind of like a free running oscillator pretty much. And so that could easily change with temperature variations. And on top of that, it's sitting right on top of your receiver. So one of the things I would do is just move that unit as far away from your receiver as possible and see if that reduces your RFI. That could be the source of it right there.
I can also substitute a battery, a 12-volt battery, to power up the computer.
That would definitely eliminate.
See whether that makes a difference. Yeah, that's
that
good.
Could make a difference. But I would definitely at least just remove it from the proximity of your receiver. Even just moving it to the far side of the box might be enough. I don't know, but try that and see if that helps.
I will. Okay. Oh, that's good suggestion. I must say, I think that the buck converters in these PoE splitters only work at a few kilohertz. So getting up to 14, 20 megahertz is a bit of a cool. And then if it is, why don't we see the other harmonics? Never mind. Experimentation is the key to understanding.
Yeah. Before you continue, John, just like everybody else, I'll just say that. John initially asked me for permission to give a 15-minute presentation. So we've got to an hour and a quarter so far, but no problems at all. It's a tour de force and quite a brilliant presentation. So whatever else you have to talk about, John, you have as much time as you would like. Because I think everybody here will be enjoying this presentation greatly. So, and then as long as people want to make comments or ask questions, we'll continue as well.
Right. Okay. Thanks for the questions and suggestions. So I'll dismiss that for the moment. Right. So how did I get that picture? Well,
You seem to shoot through a few slides in seconds, and after what discussion a second ago, you just disappeared to the end. You might want to go backwards a few
There
slides.
are a few slides at the end which I didn't intend to show. No, that was it, actually.
Oh, okay.
Well, that's not quite it. I intended to sort of give my ideas of what I would want to do for the future, which basically means, for the moment, is working on this program which I call Easy Cold QC. So I'm going to fire that up now.
That's right. You talked about giving a demonstration. You said.
I did. Right. Do people see a new window with a purple banner on the top?
Yes, we do.
Yes.
Okay, that's good. So this is my program, and I'll show you how it works. Okay, so I have now collected quite a number of files in this directory on the acquisition computer, actually. So to load the file, you just drag it into the window there, and it takes a little while to. Because I'm going to have a Bill Gates moment, I expect. So, let me take you through this. At the top, we have information relating to that file. For example, the latitude and the longitude, and the other information that I've put into it, the antenna ID, Yagi 1, and the LNA, which is a NOAALEC Sawbird H-Line, and things like that. The frequency ranges, both for the reference and the signals, the gain, SDR gain and easy cold gain, the bandwidth that I'm currently using, the integration time, which is now 50,000. One of the things that I work out is the efficiency of this. From the sample rate coming from the bandwidth, you know what the sample period is. That's in nanoseconds, so it's 416 nanoseconds. You know what the trace length will be from the number of samples, and that works out as 1,700 odd microseconds. You know the number of integrations that you're doing that, and therefore you can work out the integration time, and that is quite close to what you see on the Easy Cold screen. So it's 85 seconds per written sample, and it knows what the time span of the recording is. In this case, it's 24 hours, and so it can work out the efficiency. This is the percentage of samples that the SDR is able to produce, which are actually going into this plot, and it's 87%, which I think is quite good. I kind of thought that maybe there was a large overhead somewhere. So the top panel is more the information related to the file that has just been dropped into this program. I have, at the bottom, I have what you might call graph parameters, display parameters really. So what I'm displaying right now is just the signal traces. The color background is the various traces in time over the 24 hours of recording, and I like to see the same information graphically. So currently here I have selected color and traces. Okay, so color and traces, but I could look at the traces alone. Okay, and I can. Every 15th is now being displayed, but I could make it every 31's a good number because it's odd. Or I could just look at the colour. So you've got this selection really of the way in which you can display the data. As I say, I like to have the overlay of traces, so I'm going to switch the traces on again. No, as I said, this is the
Now,
signal.
where did the color information come from?
Well, it's the
Is it a representation of the blue intensity, the power?
yes, it is.
Oh, okay.
This
All right.
this is now your easy coal plots are 90 degrees rotated relative to this, but this in every respect is very much like the easy con displays which showed. No,
Well, I'm quite impressed with the program. How did you whip it up, or does it come from Seismology World?
No, it's my own. It's most of the software is my own, including the graphics.
Oh, neat. Okay, I like it.
It's written in Java. I've been playing around with Java for about 30 years. And I've had reason to put together programs a bit similar to this from time to time. And so this is sort of built on that kind of experience. Okay, so I've got the signal data here. Other options are just to plot the reference data. So if I click on here, it's the reference data. And for signal, I selected to use blue traces. And for the reference, I've got green. And you can change this. For example, I could do this. I hope this is going to work. These work. There you go. So now the reference trace colors are in red. Okay. So this is fine. I can interlace the signal and reference. And I think on most of your displays, Ted, your color displays are interlaced in this kind of way. So signal, reference, and so on. I can change the palette of the color. I'm going to do that later. And I can change the gain of the traces. So if I put it down to 2, for example, you won't have quite so much lateral movement. Now this data is full of spikes, not just the DC spike, but these other ones. And so I've built in some despiking programs. And initially I thought, oh well, you only need to clobber one sample spikes, and that was true more or less when I was using lower integration numbers. So but I find that I need to iterate around that several times in order to get an acceptable suppression of these spikes. So this is one iteration of this spike removal. It's a bit slow because it's actually quite a large file. The automatic scaling changes, so the colors change, and you can see that the spikes have now got reduced in amplitude. And if I do more iterations, I found that, actually I've just programmed this up this afternoon, the 10 iterations actually works really well to suppress these spikes. There you go, almost lost. Okay. Obviously another plot item that we want is the ratio between signal and reference. So you can select that here. So we're now looking at the ratio. So these are very similar to the plots that I showed you from EasyCon. And you can begin to see the H-line signal here and here. Right, there are other things you can do with this. One is to normalize, go from trace to trace and normalize it. I've got more than one way of doing that. I've got working on, well, first of all, I should say that there are actually 2 measurement windows which you can have or select. Here they are in a sort of it's like washed out white, transparent white. One up here and one up here. And I think it's good to have these 2 windows available which avoid the H-line signal so that you're not being affected by the H-line signal. Of course, you are being affected by this this RF noise. So the normalization method is either none or I won't go to peak value, but the mean value. But the one that I use is mean and level. And what it does, it forces... okay, I'll select this. I try and put in helpful feedback like that. Oops. I don't get it completely right. So mean and level makes the mean level in this gate equal to the mean level in this gate, and therefore takes out any overall ramp between these points on the traces. So that's mean and level, and when you do that, I think you might be able to convince yourself that the H-line signal is coming through a bit stronger. Okay, of course, how strongly you actually see this is very dependent on the palette range, the values that the palette range sees. So I have a couple of parameters here, a high percentage clip and a low percentage clip, which will disable a certain percentage of the high samples and the low samples from going into the automatic gaining. So I think I need to actually put this up to 120 or so. And then, do we see this a bit better? Perhaps we do. I hope we do. There and there. And I think this needs to go up to about 110 as well, something like that. This is very much suck it and see. And you just select the parameters which give you basically what you want to see. Let's put that up to 140. Yeah, there you go. So now we're seeing the H-line signals coming through with more color intensity like that. I don't like this palette very much. It's rainbow, but I've got one which I think is better. It's called Heat Map. So we'll change the color palette, and now this gives you more or less what I showed you in the presentation, I think. There's still quite a lot of noise on these traces, so you can apply some filtering. I have only one method implemented to, and that's a boxcar. So that's basically a running average. So that the minus 3 dB width in kilohertz is 50. So that is filtering in the frequency domain. But I can boost that up to, say, 200, and then you get a smoother result. There you go. There's a smoother result. And having done that, I might want to tweak the clip values again. Let's put that up.
And this last filtering is done just vertically along what you call each trace, I call each sample?
Yes, currently.
Okay.
Currently. I mean, obviously I'm going to try some lateral filtering as well at some stage, but I haven't thought very strongly how I'm going to do that.
And the lateral would be from sample to sample, pretty much like in time. Yeah, thank you.
Yeah, that's right, yes. So let's show... So there we are. This is pretty much the plot that I showed you on the presentation. I haven't yet got around to the more sophisticated things of showing how these signals relate to galactic longitude and latitude and all that sort of stuff. That's to be honest, I think I might try and go back to Easy RA for that, because the displays coming out of that seem to be very nice. But I have to get the output from this into a format which not EasyCon, but one of the other programs, all the other programs can absorb. And it's not for the first time I've come across these .npz files, I think they are, .npn, which seem to be a Python compressed file.
It's a compressed file, yeah.
Yeah, for arrays of data.
And Ezra uses them simply to, record in a galactic plane from many different, what were your radio spectrums look like in a particular part of the sky? I want focus just on the galactic plane. And so I put them in an NPZ file.
Right, yes. It seems, from reading about it, it seems to be a very standard format for transferring information from one Python program to another. But it is very Python-esque.
It is. It's all binary, yeah.
But I read that in Java it is possible to read and write these files. But whenever I get into sort of mixed operating systems, life becomes very difficult. So there's a bit of trepidation about that. That's more or less everything that I wanted to show you. Are there any questions?
I suppose I have a list, but let me start off with we see faint blue
Sorry,
lines
Ted.
coming
Before you
down.
ask any questions, there, Ted. I think first of all, all of us would like to thank John for quite a spectacular presentation there, and this is going to be some amazing resource on the BAA YouTube channel for future generations to look at. So thank you very much, John. Indeed, much appreciated.
You're welcome. And I'm hoping that in September there'll be more.
But I'm going to take with a pinch of salt the next time you ask for a 15-minute presentation window.
Well, I'm not sure that I asked for a specific time. I think you suggested that. I'm sorry if I've gone on longer than.
No apologies. No apologies needed at all. It was spectacular, and just to say that if you want to speak, have a presentation like this again in September, then or any other time, then we'll happily create the space for you, because I think these are really quite amazing, and thank you very much indeed. So to pass over to the floor now, starting with Ted, for any questions or comments that people would like to make. Ted, all yours.
Excellent. Oh, no, you got to keep your graphs up.
Okay. Well, I'll go back to sharing then.
Because we're going to be probably pointing to them, or at least it's easiest to describe when they're there. That one's a good start. Ezra was simply my exploration of trying to figure out this hydrogen stuff. I encourage all kinds of other methods. It's great. What fascinates me here is you had wiggly vertical blue lines before, and now they're kind of straight. It had something to do with you sampling in two parts of the spectrum. We saw bands vertically along here, horizontally across the page, but up high and down low. And what was the math you did there?
Right.
Here's one of them.
Here's two of them. Okay. These are simply sampling gates, and I can vary the size and position of these. There are a couple of, I think.
So I'll call them bands, because really they are kind of spectrums. You are choosing that much, and what are you doing? Take an average, and now what do you do with it?
Within each of those windows, I can measure various parameters of the, what I call them traces, of the traces along. For example, the mean value, or the peak value, or the minimum value. I've got routines which do that. And then I use those values for trace-to-trace equalization. And the method that I have at the moment is called mean and level. So what it's got nothing to do with the actual display of the traces. That's simply a display. And I can turn those off if it's a bother.
Yeah, it seems to me that the vertical traces were representative examples on a periodic basis.
That's exactly what they are, yes. Yeah. So, and I've chosen to display every 31st trace here, but I can make it much tighter, say every 5.
Just to confuse our language, I think of them as tracer rounds, as if I'm shooting bullets or something. Yeah, okay, excellent.
Okay.
But now they're very straight, whereas before we saw the 3 humps of the frequency response.
Well, remember we're looking now at ratio plots. So, to a large extent, those 3 humps have disappeared in the ratio.
Because you're dividing what? The antennas by the reference in my language?
Yes, exactly that.
Oh, okay, all right. So you flattened them out, but yours flattened out pretty nicely. I guess that means the same frequency responses were on those 2 antenna and reference signals. Okay, that's what I was trying to do, but mine don't come out perfectly straight all the time. And of course, they always have a slope to them.
Yeah, Ted, I think he's doing a second thing there after he does the antenna divided by reference. Then he's taken empty trace on either side of the hydrogen realm. He's taking averages of those and leveling. He's normalizing and leveling. That's what he's doing.
Yeah, but I do that way off in ANT-XT stuff also. I notice the edges of my spectrum where you've clipped it. This is all my language. Where you've trimmed it off, and I take those two and make it flat. But yours is even kind of smoother. It may just be that your radio's acting differently. All right, excellent. This is good. We are walking in similar paths.
Yes, very much so. Yeah.
Keep going. This is fun.
Yeah.
Now, officially, we're supposed to subtract between two signals. You know, that's what the math means. Did you do that, or did you divide?
Here I'm dividing. I could put in a subtracting option. Be easy to do.
I don't know. Mathematically, it makes sense that you divide. That you subtract. That way, you're just offsetting some energies or noises. But indeed, I find it better, or a prettier picture anyway, to divide, which I guess is a normalization. That's why quickly all my Ezra stuff becomes very relative instead of any kind of absolute measurements.
Well,
it kind of comes out with the same patterns, though.
Yes, it should do. I'm trying to think why one, theoretically at least, why one would be better than another. Perhaps I ought to implement it and see what actually occurs.
These were things that happened along my journey, yeah.
Yeah.
It'd be fun if you could explore it as well.
All right, I'll think about that.
And then the other big question was, you said if we make this, I call them samples of only so many readings, you had 10,000 for example, we saw noise, sure enough. Is it the same mathematically of adding up smaller integration samples later, even after all the square roots and summations? So I never knew if I was actually getting the same signal by later combining smaller integration samples.
I'm going to give a quick answer, and I hope it's right. All this is linear, and when you have a linear system, you can swap the order of processes. So summing inside EasyCol is exactly the same as summing outside EasyCol.
So that's treating them as power measurements. Okay.
Yes, I know. But
and yet, of course, originally way down in EasyCol, I'm recording time measurements of voltages and then running an FFT on them. That's on the very last page of EasyCol, way down in the bottom where the loop runs most of the time.
Yes, I found it. And I think what happens, well, I'm pretty sure that what happens is that you get a sample, one of your 200 or 50,000 samples, and then that goes into the FFT. It's an IQ signal, and what you get out is power. And then that is then added to the next power trace, and then the next power trace, until you build up your 50,000 or 200,000, whatever you set as the integration number, and then that gets output. And from
I'm not sure that's the exact math, because
all right.
I'm trying to think if I do the square root before this summation you're talking about. All right, well, that can be done offline much better.
Yeah.
This is fun. Other questions from other folks, please.
Remember, this is quite smooth because I've actually applied quite a lot of other processing. For example, this boxcar filter, if I take that out, for example, you'll see that it makes a a difference to the amount of noise. So I'll switch it to none, so there's no filtering coming up in a minute. There you go, much noisier. Right.
Oh wow. Okay, now
Yeah.
I see the noise pop up.
That's right. Yeah. So let's go back.
But the shapes are fairly flat. You know, fairly straight lines vertically. Okay.
Well, this box, it's just a running average, so running average is quite good at taking out high frequency noise and leaving the average. That's what it does. Now, I don't like boxcars very much, so I'm going to implement a Gaussian filter and something else called a Savitz-Golay filter, but I haven't done that yet.
Such a menu. This is cool. Yeah. I put some filters on each sample spectrum to try to flatten it out and get rid of the noise spikes. And then later on, I did other filtering, I think when you're all done, and over time as well. So that's more like an image and smoothing the image.
Yes, you could smooth that image in both directions simultaneously if you wanted to. And you don't have to use a linear filter. You could use a median filter or what they call it, alpha weighted, I think, where you only take the central, the most common. It's a sort of halfway between a median and an averaging filter. Yeah, I mean, this kind of thing was my life for 45 years. So I ought to be quite familiar with it. And remember, there's the despiking too. This despiking option here. If I take that out as well, then we get back to, yeah, bit of a mess really. You need this extra processing, as you know, Ted. Right. So every time you use a noise reduction process, despiking or Gaussian or boxcar filtering, you have less noise and your traces will look more vertical because you're taking out the noise.
Questions from others too. This is fun.
Yes. Is there anything in the presentation that I ought to go back to? I think you probably should leave it there and let somebody else have a go. Because it's 10 o'clock nearly.
I had a quick question. You initially said you had a Wi-Fi microwave connection, and that's a beautiful Yagi construction you made there. But I'm just curious, why didn't you just try to use the Wi-Fi dish that you had already on hand?
Well, I might do that in the future. Well, first of all, it's only 80 centimeters wide. Secondly, I don't know how to engineer the feed from it. And thirdly, I just like the Yagi design. I just thought it was aesthetic.
Is it an offset dish, or is it a straight spherical microwave dish?
It's a spherical one with a solid reflector and some kind of energy collector. And I think it operates at a much higher frequency than we're operating here, or when it operated. Yeah, I could think about trying to repurpose that. Then I have to find a new pole for it, that's the thing.
Has anybody else got any comments or questions they'd like to ask?
Well, perhaps I've got one question. Who else uses Yagi antennas?
Well, I do have one of Alex's.
Okay. Do you like it?
Well, at the moment, I've got a number of other telescopes running, so I haven't ever really sorted out the Yagi properly. But done a proper map with it anyway.
Yeah.
So, but I've got it there too. It's just been replaced at the moment with something else.
Okay.
But I mean, it's certainly conveniently sized and shaped, and he designed it for people who perhaps dependent with things like very small spaces. Perhaps even just a balcony area, and it does that job very well. I have later on, either today or perhaps at the next meeting, depending on where we do it, I've got a little slide that shows the gain levels on the different types of antennae, so I can give a comparison between one of these Alex Petty Yagis compared to other options.
Yes, so in the more distant future, I might find myself having two antennae working side by side.
Well, yes, I mean, certainly if I've got 4, so it depends on how much how far you want to go to. I mean, you're producing some excellent results there by the looks of it. So whether you're unlikely to necessarily get better maps by using different types, but what you will do is be able to compare the performance of the different types for your own interest as much as anything.
Yeah. Yes.
John, you took great care to get the size of the elements accurate. Is that important, do you think?
I'm not an expert on antennas. I just did what Alex said. I've used this process of making jigs for grinding down metal parts before, and I like it very much. For example, I've also got a jig for squaring off there are 2 aluminium spaces actually in the system, and you want to have square ends to those, so I have a jig for making sure that that's flat, ground flat.
Right.
And also exactly the right length. The nice thing about a 3D printer is that you can specify the dimensions, and what you get out of it is very close to what you specify.
Yeah, if it's any indication how sensitive the size and spacing is to the performance, I mean, you just tightened that one nut a little bit, and it drastically changed the performance. So there's that fine tuning aspect. And I've played around with Yagis a little bit, not the circular design that Alex did, but I just made like a quick and dirty linear element Yagi out of a yardstick and some pieces of solid wire, and messed around with that a little bit about a year ago, and I did find it was very sensitive to the spacing. I mean, you had to get that right, or it made a big difference to the overall performance. So.
Oh, right, okay. Looks like Colditz. Yeah, I mean, things that go around my head are, is it important to have round elements or rectangular ones? I guess if you get the dimensions correct, it doesn't make much of a difference.
Thanks.
Okay, shall I close down now?
Okay, well, thank you very much indeed for an excellent talk. And having looked it up while you were talking, I must apologise for suggesting you said that your talk would only be 15 minutes. That was incorrect, so sorry about that. But either way, it doesn't matter. The talk was brilliant, and I know we enjoyed it very much, and all of us will be looking forward to the next one. Right,
okay.
Well, regarding where we are at the moment, we're now at 10:05. I'm very happy to continue with this meeting for anybody that would like to. A number of people I know will end up leaving, and that's absolutely fine. I will send a new meeting date out for next month for those that do have to leave. But if anybody who's here would like to present, then they're more than welcome to do so. So I'm going to go through everybody one at a time. See, so Andrew has had to leave. We have Jason here. Hi, Jason. Would you still like to give us a guided tour of the kit that you're making?
Yeah, let me. I'm on a laptop here, so let me just kind of pick it up and move it around here. So I've been sitting at my desk at the window, and there's my SDR, my AirSpy Mini mounted to the heat sink, and the reason I do that is because I'm doing drift scans to try to
sorry,
detect,
can I just, forgive me, can I just explain to everybody else who might be just looking at a tiny picture of you on the screen at the moment. If you hover over Jason's window or his little square with his name on it, and you right click on it and then left click on pin for me, that will bring Jason up as a large picture on your screen, and you'll get a much better view. So hover over his little picture, right click on it, and then left click pin for me. Then I would say that when he's finished, you will need to go back on his name at the bottom left, click on that, and then unpin to be able to see what comes next. Okay, please continue,
All right.
Jason.
Yeah, so again, the reason why I'm using a large heat sink is not because it requires cooling, but because I'm doing drift scans over, an hour and a half to 2 hours at a time to capture the faint hydrogen signals from M31 and M33. So we're talking about signals that are so small that drifts in the background and changes, slight variations in the background slope response due to temperature make a huge difference. And so keeping it very temperature stable as much as possible has helped reduce the post-processing headaches. But I have my RF cable coming in the window. It's probably washing out because it's very, very bright. But out the window you can see my little mini dish in the yard. And in fact, I'm going to go ahead and just take a little stroll outside. And so this is my big, what's going to be a 3.5 meter dish. It's at the moment I'm still in the middle of construction. I've run into some issues with the plywood delaminating because of the weather here, because I live in a high desert, and occasionally in the spring and summertime we get some spikes in humidity where it goes up to what is normal for most other people, and those wide variations in humidity and temperature tend to do a number on the plywood, so I've had to do some repairing. But over here is my 1.5 meter dish, basically the same design. Let's see if I can. Everybody see that? Yeah, so it's basically the same design as the larger one, and this is also basically a refined version of the first dish that I built back a couple years ago when I started this quest of trying to detect M31 and M33 with a small dish. And what I've done is my dishes are basically giant inverted umbrellas where the structural members are parabolic profiles, ribs made from plywood, and then I have them attached to a central ring that slides on the poles in the center of the base, and those are attached with PVC pipes, and so the whole thing folds up like an umbrella. And my reflective surface is aluminum window screening, and the reason I chose to go with that, especially now that I'm in New Mexico, is because we get some pretty brutal wind here, and it makes it pretty permeable to the wind, so I can leave it set up more often and not have to take it down just because we're having a little bit of wind. But it also, because it's an umbrella type design, I can take it down within 5 or 10 minutes if weather's getting bad, or if a storm's coming or something. Just real briefly, I'll share my screen and just show, let's see, entire screen, and I'll just show the results of the ongoing drift scanning that I've been doing on M31 and M33. As you probably saw when I took the camera outside, my dish design is very low tech with regards to the mount. It's literally just a tripod made out of large steel bolts mounted to a flat base. So I am drift scanning. It's very low tech. And that was actually one of the design parameters. I wanted to make this thing really simple and do my observations with a very simple method. I now have I now have 12 days of drift scans for M33 and 10 days with M31. So here's my M33 profile. So the top figure is from a professional survey, a published professional survey that I was using kind of as my reference, and then the bottom plot is the result of 12 days worth of drift scans, and then the other one. So this is 10 days on M31, and again the same kind of thing. I was actually really surprised that I could get anything at all with a dish that small, but it was kind of like a challenge. It's like, okay, let's see if we can get anything with a 1.5 meter dish. 2 years ago I succeeded with a 3 meter dish, and once I kind of had the process down and kind of refined the way I built the dish, my thought was, okay, let's see how small we can go and still make it give us any kind of meaningful results. So now, granted, it does take a long time on target. I mean, 12 days worth of drift scans is about 10-ish hours of integration time on target, so that's a lot of integration time. But when we're talking about signals that are really, really tiny, but it is possible. One of the things that I noticed on John Savage, on your presentation, some of your RFI spikes that were definitely external, that seem to be periodic in frequency, they look very similar to some that I periodically see on mine as well. And based on some early testing I did where I kind of was moving my antenna around and closer and farther out from the house, I'm pretty well convinced it's my Wi-Fi router that's generating that, which would make sense. You would expect that there would be periodic harmonic content from a lower frequency digital kind of device. But what I've also noticed is, at first I thought I was going to have to remove those spikes in pre-processing before I did my post-processing. And what I found was, generally, if I moved it as far away from the house as possible, they were minimized. But even if they were visible, because they were so constant, when I did my background correction so in my case, I'm correcting background using off-target sky near the object. So I'm using pre and post transit data as my background reference. What it did is it suppressed the Milky Way signal, which in comparison to these external galaxies is huge. And then it also suppressed any of that RFI that was constant. As long as it was present in the entire scan and it didn't change, it actually suppressed it pretty well. So I guess that's about all I got. I just kind of wanted to give you guys a little show and tell of what I got going on in my backyard. So,
Well,
on the same point, Jason, I find that when I adjust for VLSR, I'm just kind of shmooing the local RFI around, and it kind of disappears. You're just spreading it around a little bit. instead of erasing it. Hooray, we win again.
Yeah. Yeah, and in my case, I do have to keep up with VLSR correction, because of the fact that I'm averaging together multiple days of drift scanning, and it changes over the course of several days. It changes enough that like John Savage was saying, higher resolution sampling is better. You can always smooth later, and that definitely is a truism, because I found the first drift scans I did on this dish were okay, but I was doing 128 bins in my FFT, and I upped it to 512. Now it's not quite as many as what you're doing, but I mean, quadrupling the number of bins made a huge difference. And then I'm doing similar to what he's doing. I'm using basically a boxcar running average to smooth the final plot, and that seems to work pretty well. The biggest thing on my post processing, which I think I'm going to go ahead and share one more time here, the background correction, because we're talking about such tiny signals. I end up using second order flattening to correct my background, and that seems to work well. If I can get away with it, I'll use just linear or offset, but usually I need second order to really get it flat. And what I do is I zoom in only to the area of interest, and that tends to reduce the complexity of the flattening that's required. So I try to give just a little bit of room on each side around the spectrum of interest, so that I have a little bit of background to set my curve to, right? And that seems to work fairly well. Now I do it kind of, I'm using Excel to do my post-processing, so I'm literally just doing it by brute force. I'm basically typing in the parameters by hand and watching the curve move, which there's probably more sophisticated ways to do it, but I'm kind of keeping it simple. So one thing that I would like to talk to Ted and or anybody else who might be interested, one of the most labor intensive parts of my post-processing is getting my data files pasted into Excel and formatted properly. And if somebody could write me a Python or JavaScript program that could automatically suck in all my data files and populate a CSV file in the right order, that would be amazing. So if anybody's interested in looking into that as a fun little side project, get with me afterwards. Send me an email or something.
So is the problem that you're getting rows where you really wanted columns or something?
Well, no, it's just that I'm using SDR Sharp as my capture engine, so I'm getting basically individual 2-column text files with a column of frequencies and a column of amplitudes, and then I'm pasting those into columns in an Excel sheet, and then I'm removing all the frequencies except the first one, because you only need the amplitude for the rest, right? So I've gotten down to where I'm pretty quick at it, but it's still pretty labor intensive, and it seems like it would be fairly straightforward to write a script that could just take all those text files, suck them in, and populate a CSV file with one frequency column and a bunch of amplitude columns to the right of it, right? And
currently, we got a solution for you already, but it will put your spectrum as a single row, followed by another row, followed by another row, whereas maybe you're used to columns.
Yeah.
Okay, but if you can change your method and put your math in different places, we got a solution for you already. My one concern is It depends how many frequency bins you have, because I think in Excel there was a limit, and you can have things taller but not wider.
Yeah, so I'm currently
How many are you using?
I'm using 512 bins.
And I think that fits. When you get up to 1024, you get into trouble.
Okay.
So we have, because I convert the IF average data over to Ezra format, and Ezra thinks of it as lines of text, and that gets read in as rows.
Yeah.
Okay, let's talk by email, Jason.
Okay, sounds good. Yeah, at the end of the day, what I find is definitely there's the noise component, the high frequency noise component that you definitely see dropping by a factor of 1 over root n, but also I noticed that the bigger lower frequency fluctuations to the background caused by just drift over time tend to settle out over multiple days as well. So like I said, I've gotten up to about 12 days on M33, and I got one more day of collection left to get to 12 on M31. And my plan is to continue to do about 4 days on each and just see what it looks like after, if I have a month's worth of data, and see how, at what point it becomes diminishing returns, I guess. So once I get my larger dish built, I'm planning to go after M101 and some of the next tier of galaxies, such as IC342, M101, NGC 2304. Some of those that are just at the next level down from M31 and M33. And I do believe, based on my results from my previous 3-meter dish, I think getting up to 3.5 meters with a little better construction, those will be within reach, especially if I'm patient and I gather, several days worth of data. So I'm looking forward to getting that bigger dish working. So.
Okay.
And that's pretty much all I have. So
I would make one comment there to both you, Jason and Ted, on the basis of the number of samples and increasing both the resolution and reducing the integration time. My main map has 2,000 samples in it. Sorry, is it 2,000 samples? Half a million samples, and 2,048 hours in it. And that was collected largely on the sort of more standard 31,000 sample integration sample numbers in the default on EasyCol. When I put that into the i5 Intel mini PCs with 8 gigabytes of RAM that I tend to use for my radio astronomy, it's a dedicated computer for the purpose, but it takes 4 to 5 days to process the data. Now I know that Ted's solution is he processes his data on a daily basis, but that's a lot of work. Sometimes I just prefer to just collect it all and then jam it through the system. So it is a question of how you're actually going to process these vast amounts of data after a while. And when people are starting off and you're only a month or so into a process with a new radio telescope, it seems quite easy, but 6 months down the line it starts to look a bit more of a Herculean effort to try and sort it all out.
But that's what batch files are for. You have to put in some characters for the file names, and you can copy and paste that too, and let the batch file do it all. But it just comes out as chunks of day processing. So we can automate that. It just hurts because you got to learn batch processing, or at least what I provide you with Ezra. So it's not as bad as you say.
Fair enough. That is a good point, and I'll accept that. Yeah. Okay. But anyway, thank you very much there, Jason. That was quite brilliant. Right. Who have we got next? Tom. Anything that you would like to talk about at all?
I found this session very interesting, so I'm just starting out. I have nothing really to contribute as a novice.
Well, tell us a little bit about yourself then, at least. You've just started. Did you say before this was your first time you've joined us in this meeting here?
Yeah, so I've been working, I guess you can call it.
So where are you based, and what's the background you have?
I'm in Saskatchewan, Canada, and I have no background in astronomy or radio frequency things. I have a very diverse set of interests, ranging from zoology to astronomy. I tend to dabble in many different things. I'm quite comfortable with various technical things, computers, networking, and that sort of thing. My limitation is coding. I don't have any expertise in coding, so I have to rely on other people to provide tools for that. So the thing that attracted me to radio astronomy was I read somewhere that it promises an endless learning curve, so that's what I'm getting in.
We're about right there. Yeah. Oh, fantastic. Well, it's lovely having you with us tonight. Thank you very much. I'd say that I'm a family doctor by background. I have no, apart from school, I have no training in physics. I have the foundation radio exam here in the UK, which means I know nothing at all of any meaningful usefulness. It's a really basic exam that just tells you the law. And Ted will tell you, because he's been my support through this whole process, that if there is a word higher than incompetency, then there's one that applies to me, definitely. So I consider my main role is to say to people, if I can make it work, then they can make it work too. So please stick with it, and we'd love to see what you actually achieve at the end of the day.
Yeah, it's slow. I've got some limitations due to family health matters where I'm in a caregiver role, so that sucks up a lot of time. But I tend to be persistent about things.
Yeah, good. We're here to support you, not here to criticise or judge you in any way. So just go for it, and you'll be amazed what you get.
Okay.
I look forward to it, and please do come and tell us about it as you do the process, because, as I said at the beginning, it's really helpful to have somebody who's just starting off talking about the different stages they're going through and the problems they are having to address and the issues they've got, because anybody else that's starting out is facing those same problems.
Yeah.
And it's like the old adage, it's very difficult to teach somebody to ride a bike when you've been doing it for 10 years. It's you need somebody who's only just started to be able to really give you an idea how to go for it. So thank you for being here, and do tell us as you go along, and do ask for help.
Yeah.
Okay.
Yeah, I read that somewhere else, what you just said, and so I come from a background of human resource development and program design and program management and that sort of thing. So that's kind of a lens through which I'm looking and also reflecting about. Unfortunately, I haven't kept a detailed diary or journal, but I think there's some value to what you just mentioned, because imagine someone from high school or junior, the beginning university years, being interested in this but not knowing exactly how to start or where to start or how to make contact. So that lens is how I view approaching this. How would someone structure a program to introduce people to this field? Because there are many of you people who know so much more, But so how do you access that at what point? And are there multiple access points to become familiar with the field?
Yeah. Well, again, do ask for help, and we're there for you. Okay, so I'll move on to Tracy now. Hi, Tracy. I noticed that behind you, up on the wall, we've got a very famous radio astronomer, one with fins and blue in colour, as he or she is not able to do any visual astronomy from where they are.
There we are. Well, I can't do visual astronomy from here. This is the basement. But I live in Colorado.
All right.
I'm friends with Jay Wilson and met Ted at the observatory in the next town over, and they set me up with a radio dish. So out of my garage, I have the very small Hackle Radio Observatory.
Do you have any pictures of your
monitoring?
Any pictures of your kit there you can show us?
You know what, I do, but I can't access them on this computer.
Oh, right, okay.
They're on my phone, so I'll have to wait and show you. But it's just a little dish out by the garage. But I do have a chart.
Oh wow!
This is some of the data, and detected my first solar flare on April 26th. So that was very exciting.
Well done. Wow.
So that's been fun, and I'm learning. I'm just starting to learn how to put the data into EasyCon. We had a late spring snowstorm, and my Sawbird was in a Ziploc bag, and it got wet, so it had to go offline for a little while. And I've since replaced it with a waterproof connector box, like John had in his picture, which was very helpful.
This is one of my SDRs, which you'll notice is not inside its box, because I found it outside just before this meeting started, and I'd accidentally left it there, and it was literally sitting in a puddle, complete with a little bit of USB extension cable. So I've dismantled it in the hope it might actually dry out. But I have no idea. I have no idea whether it will or not successfully.
Do you have an air fryer?
An air fryer? That might be a good idea, actually.
On the yogurt setting.
Oh yeah.
For 3 hours, and it'll dry it out.
Really? You've obviously been through this before.
You can't do it in an oven. The oven will boil it. It will cook it. But if you use an air fryer pot or a dehydrator, if you have a food dehydrator, and put it in there, apparently you can. So I did. I put mine in the Ninja pot for 3 hours on the yogurt setting, on the keep warm setting, same setting. So about 110 degrees, and it dried out. It's working now, so it seemed to have worked.
All right, well that's interesting, because there's been some discussion on the SARA mailing list about, on the British Astronomical Association mailing list, or one of the mailing lists, about muon detectors overheating and stopping working, and some discussion about whether they actually had long-term negative effects with going over 65 degrees. But you're telling me that we can stick one of these things at 110 degrees. So is this 110 Fahrenheit or 110 centigrade?
Fahrenheit.
Oh, I just suddenly remembered you have strange strange things there in the USA.
Yeah, it would be Fahrenheit, so that would be much less in centigrade. Would that be about 80? Yeah. So
I'm sure you would totally agree with me that America should go over to centigrade and drive on the left-hand side, and perhaps have kilometres. Would you agree? And get rid of pints and gallons.
No, we're not doing so great driving on the right-hand side, so maybe.
well, some parts of America are adopting driverless cars. It does worry me that you might buy a car from somewhere else in the world that's actually expecting you to drive on the other side of the road, or is calculating things in kilometres when you've got miles there, and that might cause accidents.
I hadn't thought of that. It could be a problem. So I just I'll try to have pictures of my observatory for you all next time.
Yes, please. Yes, please. And some of your initial
Thank
data.
you.
Some of your data, even if it's only a simple slide, it'd be brilliant. But again,
Yeah.
don't get stressed about it in any way. You know, if you want to do so, if you feel very stressed about it, don't. But it'd be wonderful if you can. Again, for exactly the same reason I said to Tom, to motivate people. It's just brilliant having people who are early on. Hopefully at all sorts of different stages, really, so that people can motivate it wherever they are. Okay, fantastic. Thank you
Yeah.
very much indeed, Tracy. That's
Thank
brilliant.
you.
Okay, now Francesco, you said earlier on you didn't have anything to talk about, but I'll give you another chance just in case you've changed your mind.
It was very interested in this meeting, and personally, I'm trying to finish my feeder. This guy is the antenna for my 3D printed parabolic dish.
I was thinking, I've seen the movie Contact, and that looks to me like it might have come out of that. You don't know what I'm talking about.
This is the boom that goes to the center of the parabola. So I haven't the 3 or 4 arms that interfere maybe with the signal. I need to finish it. I must mount the connector with the probe. I must choose between an SMA connector or probably an N connector that is more stronger, because I want to connect directly my Sobird and AirSpy.
Can you just remind me, looking at the size of that boom, remind me, how big is this dish that you've built?
At the moment is 1 meter and 20, but I plan to expand to 1 meter and 80.
Show us this boom. Show us this boom again.
Yes.
Pull this boom up again. Mamma mia!
Yes.
Fair enough.
This white piece is only a reduction between this boom and the antenna.
All right, fair enough.
My problem is this antenna is too much wider for my 1 meter and 20 dish. So for this reason, I think I will adopt the solution of Conrad to make a screen around the antenna, around the dish, to screen the spillover from the air.
Yep. Okay.
Francesco, question: what is the focal ratio of your dish design at this point? At 1.2.
0.4.
And then when you increase it to 1.8, it'll be like what, 0.35 or something like that?
Sorry, Jason. No, with 1.2 meter antenna, the ratio is 0.06. And when and when I expand the antenna to 1.8, it will be maintain the same focal length, but the ratio will be 0.4.
Okay. Yeah.
With 0.4, the antenna will be the exact flare for this diameter dish.
Yep.
So momentarily, I will solve to extend with aluminum mesh, window mesh, the smaller dish. I will satisfy if we'll see a little hydrogen trace. Okay. Thank you.
Okay. Thank you very much indeed. That was brilliant.
Okay.
So,
Thank you.
hi Ted. Would you anything you'd like to talk to us about?
Wow, thanks for the opportunity. No, we've been chatting all about the things enough on my side. I'll hit you with new ideas another time. This has been fun.
There's one question I wanted to ask you. Did you do a version of EasyCal that works on AirSpy?
There's one with soapy drivers, and I suppose GNU radio.
Okay, so the soapy drivers one, if you want to use it, if I want to use it with, try it with an AirSpy, will it automatically pick up the AirSpy, or do I need to put in a setting in it to tell it that it's got AirSpy?
It was programmed to use the soapy driver for AirSpy. It wasn't so automatic. Trying to think. Oh no! But eventually it was automatic. Remember the one you used for your B210?
Yep. Or is that the same one?
If you just put it, I think if you just put an AirSpy in there instead in hardware, it will say, "Oh, that's what's available. I'll use that," and so it'll just grind. So I think you already have the program out of your. You have collections of antennas, but you also have collections of programs.
Oh, just after Jason's comments earlier this evening about the advantages of an AirSpy, I thought I have one, and I thought I would perhaps just give it a try and see what the difference was in terms of the signal coming out.
My problem was that the frequency spectrum ripple, the shape of that spectrum,
yep,
was just not exactly flat. It was kind of curvy, and then it went way up on the right. So there were awkwardnesses. But if you used a reference file to remove that strange shape, then that would be cool. You could kind of remove that same shape, that strange shape of the frequency response, also by using SDR sharp into IF average, which would then, and that would allow you to remove that background at the very beginning.
Mm-hmm.
So you make a background sample, I guess, to subtract from all your later samples. References simply do that on an ongoing basis, but SDR sharp method allows you to remove it in the with one sample in the front to remove it. There are other ways. It's kind of just like the. Anyway, there are ways to make references using one sample as well, and maybe that's a whole lot easier for you. Where you go, what's it called? EasyCal reference. Is it maker? I don't know what it is. And you put in a negative number for the sample that you actually want. If you want sample 88 to be your background, you could put in blah, blah, blah minus 88. And it's not a subtraction, it's just a tricky way to get 88 in there with a second meaning. Is that too much information? We could talk by email.
No, that would be brilliant. Yes, I might well come back to you on that.
I expect you will. Yes.
Yeah, you know me. You know me very well. Oh, thank you very much, Deb.
I like all the exploration. This is good.
Knowing me, come back at a real sort of basic first principles, where you have to use words with one letter in them. 1 + 1 = 2, Andrew. Take it from there. Yeah. Anyway, are we too late for anybody want to see my little bit I'd prepared, or I could always put it out to next meeting if people feel they want to go away, or do you want to hear it now?
Hey, it's not even 4 o'clock in the afternoon. What's the problem?
Okay, fair enough. Right, so just check if I got it pulled up. Wait a minute, so I just need to share my main screen. Let's get rid of this. Oh, here it is. I've got it. So this is only an hour and a half long, so it won't take very long. No, not as bad as that, not as bad as that. Okay, right. So I don't know whether everybody here has heard of the Horn of Plenty. If you type in Horn of Plenty on Google, you come up with all sorts of things going back to the Greeks, which have got nothing to do with what I'm talking about tonight. But you will have heard of SETI, the Search for Extraterrestrial Intelligence, and they came up with this idea of the SETI Horn of Plenty. And I'll tell you more about that in a second now, but it's a particular design of a hydrogen line antenna, which is a little bit different from the ones that we talked about earlier in the evening, or you might have seen elsewhere. And it will be interesting because it's got some benefits over other types. In other ways, it's no real different to anything else, but it has got some particular benefits, which we'll see in a minute or two. So, getting back to horns, I was trying to look up a little bit of background to these things. So this is where I don't have any expertise on this at all, but I was trying to look it up. So this chap, Heinrich Hertz, in 1888, hence obviously we know where the term Hertz came from in terms of frequencies. This obviously came from his name. So he was the guy who first came up by putting a primary conductor in the focal plane of a large concave parabolic mirror. And so he the first one really to develop a microwave gain antenna. Obviously 1420 megahertz is at the lower range of the microwaves part of the radio spectrum. And then there was this chap, Bose, in 1897, who did the next clever bit of actually getting the waveguide, which is we've seen a container a little bit earlier from Francesco there, and he flared it out, and you can see the Bose design there on the right hand side. See, if you look over at the right, you can see there's that little metal structure there. I don't know if you can see my cursor. Maybe can you see my cursor? Is the cursor visible? Anybody?
We see your cursor
right
waving over the thing on the right.
So you've got the waveguide here, and it flares out at the bottom. So this is the flare bit here at the bottom. So it allows you. I never really understand this business of I and Q, but it's apparently a low Q structure and gives you a good gain. Thereafter, people started to use these waveguide horn antennas. So this is an example of a horn, really, that waveguide. And including the famous Marconi, who was all to do with telecommunications, the telephone, etc. And he managed to demonstrate in Britain that he could do microwave communications over 4 miles, which is great. But believe it or not, it wasn't until 1951, 1960s, that these type of things were applied to radio astronomy. And then there was this chap, Harold Doc Ewan, very famous over there in the States, and he created this horn, this rather big thing here. Some people believed we used it for drinking cups of tea out of, but other people felt that he was collecting microwaves. Anyway, note the size of it, rather large. Possibly not the most convenient antenna to build for a backyard amateur radio astronomer. This is the same horn with Ewan himself. It's now at the MIT Radiation Laboratory, where you can go and see it yourself if you want to.
That horn was on the 3rd floor of the university building. So
was it? Yeah. So
he was up in the air.
Actually, where you see it now, it's been permanently placed in front of the Jansky Center at Green Bank. That is actually the Green Bank.
I was just about to correct that. It was originally at the MIT Radiation Laboratory and is now at the Greenback Observatory. My apologies for that error, and thank you.
In fact, I have a picture of myself and Lisa in front of it.
Brilliant. Maybe in a second or two you might want to show it to us. Anyway, so I apologize for that error, and thank you for Jason correcting me on that. So his gain was 24 dBi, and it was 10 feet long. So SETI decided they wanted to copy this for amateur use, but because of the size, they decided to just shrink it down a bit, and it was literally just scaled it down. So it was 4 feet long and 3 feet wide. So that, for people who speak normal language, that's 1,200 millimeters long and about 950 millimeters wide. They also based this, apart from just size, they based it on the fact that it performed very similarly to a 1 meter dish, and also that at that time they did it, which just shows how long ago this was designed, because you won't get it for this price now. But that time they could actually get galvanized sheet steel at $10 a sheet at 3 by 4 foot sections. I bought some galvanized steel recently, and it definitely didn't cost me $10 for 3 by 4 feet sections, definitely. But anyway, they basically just scaled the dimensions down, and this, when they calculated it, was going to give a gain that was only 3 to 4 decibels below the Ewan horn, so it was going to be pretty close to it and give a pretty reasonable horn for collecting hydrogen signals, and even potentially for looking for SETI signals. This is their original set of calculations, and it shows you the differences between different sized, or at least different frequencies, and what you would expect to get. So there is some, as the frequency goes up, the gain goes up a bit, as you can see, but around about 1,400, we're looking at sort of 17 to 18 mark, or 17 to 19 mark on dB or dBi. These are the dimensions as a plan, which I printed out in order to be able to make mine. As you can see, so it works out 36 inches or 3 foot wide at the bottom, and actually 47 3/16 at the bottom, which is including the waveguide bit at the bottom. So essentially the 4 foot there is down to the monopole where it enters into the side of the horn. And you can buy these what they call chassis connectors, which is the one that's on the left hand side there, very readily available off hardware sites such as Amazon and elsewhere, which you can easily screw, as you can see there on the right hand side, you can easily screw into the side of the waveguide component of your horn, or wherever else you're making, and on the inside then you can solder either a piece of copper wire or a M2 piece of copper tubing seems to work slightly better, or brass tubing on the inside of an appropriate length, which you can see there is about 4.6 centimeters, 46 millimeters, or 1.8 inches, is about right for actually collecting hydrogen. These are some pictures which come from SETI, they're not mine, but they come from the construction that they did of their original prototype. So it gives you an idea of what this thing looks like when it's put together, and a rough idea of its size. And if you look at the picture at the bottom left hand side, staring down the centre there, you can see the monopole right at the other end. There are various ways of actually mounting that monopole. In this particular prototype, they've just basically drilled a hole in the side of the horn and put it on there. Alternatively, you can actually build a section at the bottom which is a rectangular with straight sections, which is probably more how you get it if you're doing getting a professional waveguide. And there you are, that's the original prototype of the SETI horn of plenty there, which shows one of the issues of building these things, which is if you're going to make it with the galvanized steel, you end up with very sharp edges at the top, so it's worth putting something on there to actually stop people from getting hurt. As you can see on the top of that one, people have made these things with various materials, and probably they're more commonly made with insulating foam, and then put sticking silver foil, aluminium silver kitchen foil on the side, and you can make a very effective one that works. But of course the problem is you don't have a very robust antenna, and it won't last very long when you put it outside. So ideal for demonstrating hydrogen, but not ideal if you want a long-term antenna which is actually going to start mapping the Milky Way. So this is just taken straight off the SETI League's website, which is really the stuff that I've already given you, that it gives a reasonably on par performance with a 1 meter dish. And the bit at the bottom is perhaps worth noting, where it says excellent broadband impedance match, so it's quite good at actually collecting a signal over quite a wide range of frequencies. And the second bit is probably the bit, and the third bit, which is probably the bit that really matters here. Overspill if you're doing transmission, but low side lobes, and its ground noise pickup is reduced. So we had a conversation earlier about extending the side of dishes to try and reduce ground noise pickup. One of the great things about a horn is it inherently has a very low ground noise pickup, and hence potentially, and often in practice, actually performs far more highly than you would expect it to do so from calculations alone. So I've had a go this last week building one of these SETI Horn A Plenty. People talk about doing it in 2 or 3 hours. Me, it's taken about 4 days to get there, cutting all the bits of steel into pieces, etc. So that's roughly, you give yourself a good week and quite a bit of time during that week to do it, and you get it back done. And here we are with my model, my wife here, giving an idea of the size of this device. So you can see that if you actually look behind Annan on the right hand side, just inside the garage, you can actually see more of these galvanized plates. In the UK, to actually get this stuff delivered cost £80, which is probably one of the biggest issues. But if I spent £160, I got it delivered free. So I ended up with 10 panels. I only needed 2, so what on earth I do with 8 other large galvanized steel panels, I have no idea. So if any of you want one, for just the basic cost, you can have one, but I mean, how are you going to get it back out to America? I'm not sure. But I'm quite prepared to sell that cost back out to people, and that would save you delivery costs. But it's and in terms of these metal things on the side, Adrian the day was asking me what they were. These blue side bits. You get these shelving units that you have in garages. So these are the metal strips that go on the side that you can set your shelves at whatever level you want. Now, if you buy those normally, they're very expensive, but I found on that great site eBay somebody who'd done some sort of commercial installation and had a pile of 90 odd centimetre cut-offs left over that he was selling quite cheaply, so I picked up a pile of those. The original SETI League horn, they used rivets to connect it together and folded the sides over, but these things allowed me to just bolt it on at the sides, so it made the construction a lot easier. And again, here's been moved to the back, and that's the mount that I constructed. Adrian was kind enough to suggest that I was very clever at making mounts. It didn't quite work that way, Adrian. What actually happened is I started making a mount, and then when I put the antenna on it, it sort of fell over to the side because it wasn't stable. So then I started bolting extra bits of wood on it, and that makes it look better and also makes it more stable. But I don't want anybody to be carried away with the idea that I actually designed it properly in the first place, because I don't work that way. And then our local recycling centre, i.e. places you go and check your rubbish, has now got a shipping container, and in this shipping container they have bits of paint that people bring to throw away, and any decent looking tins of paint to put in there, and if you wanted you can have it free of charge. So I popped down there and picked up some fencing paint for nothing. So and the wood from here actually came from one of our neighbours is doing an extension and had some wooden pallets, so I picked up one of those and took it apart. So again, just recycling old bits of material for nothing, apart from the galvanised steel plate. And here we are, that's with the with 2 of the other hydrogen line telescopes and something in the middle which is a TV minicaster, which is going to be used hopefully for maser observations if I get it working. And there's the Alex Pettit Yagi there on the right hand side. So oops, we're gone. Oh, hang on, we're going the wrong direction. Just a few more pictures of manufacture. Now in my particular case, I've used some time ago I actually managed to pick up relatively cheaply one of these professional WR650 waveguides. Now these normally cost an arm and a leg, so I was very lucky to be able to pick it up at a decent price. it works quite well, but you don't need to use one of these. And if you look back at these pictures here, you can see why I've got those little, if I show my cursor, these little metal strips down the bottom, so they're on the sticking out so that they actually can screw onto the holes on this professional one. And here we are, it's now in place next door to the other telescopes with the barbecue. And then I realised it was going to act as a really good collector of water, so I put a plastic sheet on the front, hopefully to keep the water out. And the next thing was how I was going to work out actually what the actual elevation of this thing was. I'd actually, for various reasons, on top of the waveguide, actually got other stuff taped on there, so I couldn't use the top of the square waveguide at the bottom. So with my calculations here, I managed to calculate, actually using signs and arc signs that took me back to school, that if I measured an angle using my digital inclinometer from the top of the flange section and took 38.1 degrees off, then that should give me the real elevation. Let's hope it works. And here's first light, which, as you can see, is at least showing some peaks going over the Milky Way, which looks good. And this was a bit stop-start, which is probably why it's not giving a terribly wonderful picture, but at least we're managing to get some element of the galactic snake coming through. A lot of improvement to do here, but where something's coming through. And then with Jason's help, we tried to calculate what the maximum gain of this thing was. So this is from EasyCol, and this shows a maximum trace. The spike is RFI. I did wonder where, this last few months, my RFI locally has gone up. And then I discovered literally yesterday that my next door neighbour for the last 10 months has had one of these air source heaters in his garden. So I think I now know where the RFIs come from. But anyway, this calculates up as 0.855 decibel above background. So I thought that's 0.855 decibels. And those calculations from the SETI League talked about nearly 20 decibels. So what's going wrong with my my radio telescope here? So that's
actually, one Andrew.
I'm just about to answer it.
Oh, okay, sorry.
so that's one side of the Milky Way. That's the other side. Sorry, that's the other side of the Milky Way. And then that's your calculations that you did to work this out. And then that's just another way of looking at the same calculations, but the bit at the top is using ChatGTP. I looked this up and learned something, which was that decibels are decibels above background, and dBi is the antenna gain relative to the isotropic radiator. So if you take your decibels of 0.73, slap it into an appropriate calculation, you end up with 22.5 to 23 dBi. Is that what you're going to say? Adrian, sorry,
Yeah,
sorry, Jason, sorry. Is that what?
Yeah.
Anything else you want to add to that? Sorry?
Basically, the gain of the antenna versus the peak that you measure above background, those are kind of apples and oranges, right? So
exactly, that's what you said to me when we were having that meeting the other day. But so I now realise there are these two completely different things, and that's why you get two completely different measurements. But it does mean that, bear in mind, this is now saying that calculation that a practical estimate is 22.5 to 23, but bear in mind that's actually based on an assumption of 55% efficiency. So that suggests that my Horn of Plenty has actually performed significantly better than the SETI League's horn. And there is one particularly good reason why that might be the case, and that is essentially to do with the quality of the filters and the SDRs that we have available now. What they had available back then was nowhere near as good. Sorry?
There's one more point, Andrew, and that's that the dBi as an isotropic reference is a theoretical measurement, because there's no such thing as an isotropic radiator. So that's a point radiator that it equally radiates in all dimensions, and so it's theoretical. And so the more practical, what you had there before, the dBd, which is a reference against a dipole, which has some inherent gain of its own, and so that's a different reference.
Sure, but the point I was making was how well did mine perform, and or does it perform? And the answer is that the SETI League were, or do suggest on their website, that you're going to get between sort of 17 and 19 or 17 and 20.
Well, that's the point. See, if you look at the scale where it says gain, and you have dBi, and then that's the isotropic reference, and then the next column says dBd, which stands for dipole, and so that's the reference for the dBi as the reference point. So it's a reference against a dipole. Again, also a theoretical dipole, but nevertheless, because the dipole has some gain inherent, that's why you see a lower gain for it, or the lower number for it, like 17. And of course, the isotropic has supposedly zero gain because it radiates equally in all dimensions, and so it would have a smaller gain. So therefore, whatever gain you have of your antenna reference is higher, the 19.9 that you see there. I don't know if that makes any sense or not.
So are you saying that the calculations which Jason came up with there are actually the dBi divided by the dBd?
Well, I'm not sure what the calculation is, because it's essentially a gain comparison against two different standards. I don't know if that makes any sense.
All right. Okay.
So you can have the standard as isotropic, and then that's it. So you get a relative larger gain because isotropic has zero gain. Whereas if you reference to a dipole, which already has some gain, well, of course, you're going to have a reduced gain from your antenna because now you're comparing it to something that already has some gain. I don't know if that makes any sense or not.
Oh, right. Okay.
Anyway,
it's basically like two different. You said two different. It's almost like two different units, really.
Yeah,
because you're just basically changing your reference point. One's
exactly.
about 2 point something dB lower than the other one. I can't remember the exact value, but it's
yeah. Whatever dipole is, theoretical gain. Yeah.
So where would, looking at those values there, Jason, where would the 0.85 that you calculated?
There's no. I didn't even attempt to connect those two numbers to each other. There probably is a way, but I just kind of I was comparing it to some of the results that we see with some of the experimental results that Alex Pettit got with some of his other different kinds of antennas that have a similar aperture. So like the 1 meter size dish had, he got, his results were somewhere between 3/4 and 1 dB above background. So, looking at the fact that your horn of plenty is roughly equivalent to like a 1 meter dish, I was thinking, it was more of like a kind of almost like a, not really a rigorous calculation. It's more of like a, does that seem reasonable? Some of his, larger antennas, and even my, my 1.5 meter dish, I'm getting closer to like 1.5 to 1.7 dB above background, and some of Alex's really nice, finely tuned, larger antennas, he's getting close to 2 or 2.5 dB above background. But but there's not really a direct link between that and the gain of the antenna itself. There is. Theoretically, you could come up with some kind of calculation that would tell you what that would be, but that's a super complicated endeavor that I haven't even attempted. So,
well, but if you're comparing then your gain versus your background might be different from my background. So that's just a relative measure.
But no, the hydrogen signal will be basically riding on top of whatever background you have.
Right, but that's my point. What is your background? And so
because it doesn't matter. It's a relative measurement. You're saying
exactly.
Okay,
well, that's my point, because that's what I'm saying. Because you're comparing it against background, and how do you define background? So, like what I'm saying, my background and your background could be different. So, but it's just a relative ratio. Whereas
It's compared to the background on your system. So
exactly.
So
what's
this
the-
level
what's the
here,
lo-
you're basically saying
But what-
it depends on whatever the noise
Yeah.
level is and all that sort of thing.
yeah,
for
exactly.
you. But when you
Exactly.
reference DBI or DBD, that is an absolute measure.
Yeah, yeah, exactly.
Exactly. That's my point. Yeah.
Yep.
One is relative. The other ones are absolute measures. But again, the DBI, DBD absoluteness depends on which one you use. Isotropic,
Yeah.
point source, which is theoretical, or a dipole, which is more physical reality. And so that's just the point. And actually, when people sell antennas, they go, "Oh yeah, it's like 600 dBi, or whatever." They just want to use the larger number, but which is correct if you just define it as dBi. But a more practical reference would be more DBD, because again, isotropic radiators don't really exist. But I don't know, maybe a black hole or something. I have no idea.
Yeah. Well, and the thing is too, you could, I mean, in reality, the best way to tell what your performance is, and to get some idea of if it's performing well or not, is to compare results against other similar systems. And that's kind of what I was getting at with what I was saying is, based on Alex Pettit has done some very careful empirical measurements on his different antenna designs, and kind of shown how they compare to each other as far as what your peak value at the brightest part of the Milky Way at a very specific, he has very specific coordinates that he looks at so that he can compare different things using the same signal, right? I'll have to go find it, but he had a plot where he showed all of his different antennas and how they compared to each other. And he basically showed the same spectrum from the same part of the sky with each of those different antennas, and showed which ones performed better, which ones performed worse. And even like the worst case, just a plain antenna with nothing else, just pointing the antenna at the sky, right? And that one only gave you about a quarter of a dB above background, but it was still measurable. You could still see the hydrogen line, which was pretty impressive, actually. But yes, based on the earlier material that Andrew, that you had, where I think SETI was saying that this horn should roughly perform about similar to a 1 meter aperture dish. That's what kind of gave me the idea of okay, we know we can see some of Alex's results for his umbrella type 1 meter dish, and it was around the same, around 1 dB or so, so your results look good, they look reasonable, right? They're in that range, just roughly in that right performance range, right? So it's, none of this was, there wasn't really a way to compare or to get, to theoretically calculate what this value should be based on the gain of the antenna. It was more of just comparing to other people's empirical results. So.
Yeah, well, no, I find that explanation very helpful. Thank you very much indeed, both of you. No, very much appreciated. It doesn't bother me that it's approximate rather than absolute accurate, because I'm not too worried about that. What I'm more concerned about is understanding how to understand whether an antenna is performing reasonably well.
There are
another experiment that I would do that I would suggest you do is do a drift scan of the sun, and see, with that you should be able to get some idea of what the beam pattern looks like, and you should be able to measure approximately what the half power beam width of your antenna is. And also that'll also help you verify that your elevation pointing is accurate.
because you can kind of point it straight at, point it at the sun and keep adjusting it until you peak out the background level, right? And then you can tell, okay, is it actually pointing where I think it's pointing? And also, they've given in the design parameters, they've given you what the approximate beam width is expected to be. So it'd be interesting to see if you measure it using the sun, what would the 3 dB points be? How, would they be 15 degrees apart, or would they be wider or narrower, right? So that would give you another way to kind of measure your performance of your dish or of your horn, right? So.
Mm-hmm.
Just as a point, they do sell reference horns and reference antennas, but whether you can find one exactly for 1420 or not, it's a completely different matter.
Yeah.
Okay, brilliant. Thank you. Right. So, what else have I got? Okay. So I did promise a slide showing the. So these are the DBIs. So with the caveats of what we've just been told, it just gives you just to get an approximate idea of how things compare with different types of dishes. Which I know that Jason there has actually given quite a bit of information on that a minute or two ago. But you can see that the 1 meter that we're talking about here is at 18 or 20. Remember when you go for a 1.5 meter dish, getting up towards the 25 mark, 2 meter dish sort of 27, and 3 meter dish up to 30 to 40, 31. But the 17 element Yagi and my 86 centimeter Ptarmigan and Triffid are down at 15 to 18. So not too far off, but it just gives you an idea of how things. So just worth saying that the Yagi technically supposedly isn't as good as the dishes, but I think the message that's come out of this discussion really is tonight is the problem with ground noise or ground coming up to your antenna, and any way that can reduce that will dramatically improve the performance of your dish, and that's where the advantage of the horn is, that it suffers from that problem to a lesser degree inherently than dishes tend to. But I guess if you add in that aluminium windscreen, so window stuff, then you might start to see the advantages of the dishes outperforming the horn. And this may well explain some of the problems I've been having with my 1.5 meter solar cooker dish. I really do need to use that window aluminium screening around it and see what that does, because it hasn't been performing in the way that it should do.
Well, Andrew, wherever you got this slide from is very informative, because right there in the middle of it, exactly describes, defines exactly what we were discussing earlier.
Yeah. I can't remember where I got it from.
Well, right in the middle, where it says DBD is reference to a half-wave dipole, and DBI is reference to an isotropic radiator, which is exactly what we were discussing, and it even gives the exact difference between the two there, as Jason had mentioned. So it explains it all in a very, very informative slide there.
Yeah, brilliant. So I said I'd mention some problems. This is the laughable bit, which is, as you saw, Adrian, I presented you with some good data there, which were coming out, at least some initial data that showed the horn was working, and then I also showed you that it had stopped working. So here we are. This bit of video shows you the problem that I had on the 31st, i.e. yesterday. And the thing to notice is that we have the trace, but lo and behold, over multiple hours, nothing's changing. And we should easily be seeing a hydrogen peak or two coming up here, even if it's a small one. It should be seeing quite a one coming up and going away again, but it isn't happening. So the question was, why is that the question? And you and I, Adrian, discussed possible ways of approaching that. So I was going to start those approaches, and I didn't get very far because I think I found the problem very quickly.
Doesn't work underwater, huh?
Here we are. Inside the dish.
Slosh.
Slosh.
Well, you know, this is funny. This is ironic in a way because Harold Ewan actually talked about, because he detected the hydrogen line for the first time with his horn as part of, that was his doctoral thesis. That was his PhD project, right? And everybody thought that it was impossible. They thought the signal would be too small to ever detect. And he said that the junior faculty at Harvard used to throw snowballs in it in the wintertime because they could smell a failed experiment a mile away. So you're following after Doc Ewan there.
Oh, if anybody can get it to go wrong, it's always me. So, but still, it's all a bit of fun. And so I've emptied it out at the moment now, but we've been raining all today, so.
So Andrew, if you drill some really small diameter holes, it shouldn't really affect it very much, and it would act as a drain for any water buildup.
Well, that is actually the question that I want to ask. Here's a picture of my waveguide. Here's my picture of the horn. I put a couple of question marks, and the question is, where do I drill a hole? And if I stick it in the waveguide, will I destroy my expensive professional waveguide?
You know, like a 1/32 drill bit or something, or 1/64.
And as close to the back corner as possible.
Exactly. Yeah, just where the water would pool, and it would just drain it out, and it shouldn't have any measurable effect on the waveguide. At that frequency, that small hole is like invisible.
Well, Andrew, my problem is I figured this problem with my WR 650. I have similar like yours.
Yeah.
I have put a film of Capton on the mouth of the WR 650. So it is completely closed. Capton is a material transparent to radio frequency, or you can build or 3D print a flange of the same dimensions and put inside, in between, fiberglass or similar material. So the transition is completely sealed.
Yeah, but you always have condensation. If you have high humidity environment, then you can always get condensation to still pool water inside. So you still need somewhere to drain, even if it doesn't have entry for like rain or something. But again, condensation from nighttime to day and so forth can still build up significant amount of liquid inside.
Obviously, you can periodically control if the inside is dry or not.
Yeah. Okay, that's an interesting idea. I still need another hole then at the bottom of the horn to let that drain as well. If I stop it from draining out of the wave, from going into the waveguide, I would need another hole at the bottom of the horn as well.
Or maybe, Andrew, if your transition is the same with screws on the back, you can leave one screw and leave it the hole. So you can drill another hole.
All right. Yeah. I will consider these various suggestions. Thank you very much indeed. That was indeed the discussion I wanted. So much appreciated, everybody, for your suggestions.
Thanks.
Oh, just to finish off, I found this picture today online. When I wanted to upgrade these things, somebody's actually providing a water-cooled waveguide. if anyone was concerned about the temperature of the waveguide causing problems. I don't know whether we would
I-
worry about that at all, personally.
I think that would be useful if that was being used as a transmitter and you were putting, like, I don't know, several kilowatts of RF through it, like from a radar transmitter or something, and then that might warm up that cavity, and you might want to cool it in that case. But I don't think you'd be transmitting it, 10 or 15 kilowatts of energy. So I don't know.
I'm not sure that my foundation radio exam here in the UK would allow me to
It won't
transmit
cover
10
it, I can
kilowatts.
guarantee. It won't cover it. It won't cover it there or even in the US.
Certainly not in the protected radio astronomy band. One thing that we have, just a few references for anyone who's interested. It's again off the SETI League website, and the one at the top might be most of interest to anybody, which is the actual article on the Horn of Plenty, if anybody wants to know about it. But one oh, that's right. Earlier on, there's some discussion about RFIs. So one thing that's worth noting, especially here in the UK, is that so obviously hydrogen line is a protected region, but it's not too far away from the cell towers, and there is tend to get leakage across, especially if you're close to a cell tower that's quite strong. So if anybody's looking for sources of RFI. The other thing is that, as I know has been discussed on these meetings before, is just to be aware of how close people are to any flat screen TVs or monitors, because they produce quite a bit of 1420 megahertz emission. So especially if you've got a computer that's close to your aerial, it might be, the screen might be interfering. We've already had some discussion earlier on from Adrian there about the effect of switching power supplies. And as I've discovered, I now realise that air source heaters are a bit of a problem, and I know people have discussed issues as well on this meeting before about the effect of the transformers for solar panels is causing issues, and we have more and more of these things. We all tend to have quite small plots here in England, so even if you've got a garden, etc., you aren't too far away from somebody's microwave emission.
I was going to make a further point. I know John was talking about the fact that the frequency of the of that buck boost power converters for voltage, dropping down voltage, and I was going to say that even though the frequency is low, you might not be coming in through the front end of the receiver. In other words, it's not necessarily coming in through the frequency that you're looking at, but you might be feeding the RFI directly into the ADC converters, which are much more receptive for the lower frequency. So you're not radiating it in as a high frequency interference, but actually having the interference being detected directly through the ADC converters of the SDRs. So that's why you're seeing it.
Yeah.
That's why you're seeing the constant. You're seeing the constant. Even if you tune the SDR, those spikes are relatively at the same place, because you're not tuning the spikes in through the front end of the receiver. They're coming in directly into the ADC, so it's just directly into your output. I'm sorry,
Well,
Jason, go ahead.
Even though it's down at, say, 30 kilohertz, that's only the switching rate. But those switches have super fast rise times, and
yeah, the harmonics
as those
are
of us
awesome.
who there's lots of harmonic content that goes with it.
The frequency spectrum of those sharp rising pulses and so forth, feeding into the inductors are just really atrocious.
So would it be worth putting your SDR into a metal container and then earthing that?
Wouldn't hurt. It might not stop it, but yeah, I mean, you're building essentially a type of Faraday cage around it, which should help if it's feeding in from some other input.
I remember years ago, I went to something called the Peak Star Party, which doesn't exist anymore. It was up in the Peak District here in England, and while I was there, I took a meteor scatter demonstration kit with me, and they had a barn where they were giving some talks, and some of us were asked to set up our demonstration. So I set up a demonstration on a table there, and lo and behold, this was going on for the weekend, and I picked up virtually no meteors whatsoever, and I wondered what on earth was going on. And one day I was walking outside the barn, and I went about 50 or 100 yards away, and passed somebody's tent, and they had a meteor set up outside their tent. And as I passed it, I looked at their screen, and it was going ping, 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 merrily away at a right rate of knots, picking up meteors. And that was the point at which I realised that the barn had been built from a metal frame, and was just acting as a Faraday cage, taking all the signals straight to ground. So didn't pick up a thing, but there we are. I don't know how much that applies to hydrogen line.
Well, it's throughout any electromagnetic radiation. Faraday's cages work throughout the electromagnetic radiation that's applicable. So
the other things we do have multiple source earthing here in this house. Would that make? I don't even understand multiple point earthing. Does anybody else understand that, and what difference that makes to whether I could create a Faraday cage or not?
Well, Faraday cage has to encompass all the dimensions. Anytime you have an open side, then it's not a cage anymore. So it has to.
Do you know what I mean by multiple point earthing?
This is for your power, for your electrical.
No, it's to do with the electricity supply in the house.
That's what I meant. Yeah, the power companies, your electrical circuit, your AC power.
Well, they take an earth, which is based on multiple earthing points, I believe, on a number of houses, and of course the ground between the houses may not be exactly 0 volts between them, so it can affect the effective zero that you get. So where you're based in your garden, your earth through the mains might not actually be the same as the zero of the earth around you. So I just wonder what difference it might make creating a Faraday cage and then sticking it into the local ground, which might actually be different to the earth.
Well, a Faraday cage doesn't have to be grounded. It just has to completely envelop the area that you want to shield from electromagnetic radiation.
Oh, really? So it doesn't have to be grounded?
So it could be floating in space, and it would still be a Faraday cage.
Oh, really?
It doesn't have to be grounded.
Oh, I got it in my head it had to be grounded. Oh, well, there we are.
Well,
I've learned something. I've learned something else.
It could be. I mean, it could be, but it doesn't have to be. As long as it encompasses the volume that you want to shield from electromagnetic radiation, then it's doing its job. As long as and it doesn't necessarily have to be completely solid. If you just only want to shield for certain frequencies, then you can have diameters of holes that are just much smaller. For example, one good example of sort of a Faraday cage, it's not exactly, but look at your microwave oven and look at the window on it. It has a metal screen with holes in it. And yet you don't get cooked when you stand in front of your microwave oven, and that's because those holes are small enough that 2.4 gigahertz microwave energy from the magnetron, that the wavelength of that in relationship to the holes in that screen in that window are just like tiny. Essentially, it looks like a solid surface to the energy inside your microwave oven cavity. So I mean, that's one example where you can shield the radio frequency and not necessarily have to have a solid surface. But now, if you were to change that magnetron to something like, I don't know, 20 gigahertz magnetron or something, then you'd be cooking yourself if you stand in front of that window, because those holes in there are significantly larger compared to that wavelength. And so it's just relative to the frequency you want to shield your electromagnetic. And of course, if you want to shield all electromagnetic radiation, then it's all solid, purely solid. I don't know if that makes any sense or not.
Yes, yeah. It does. Thank you again for the explanation. That's good. Well, thank you very much, everybody. I think that's been an absolutely wonderful meeting. Is there anything else that anyone would like to say before we close the meeting now? No? Well, I will send another date out, which let me just check. Yeah, which will be the 6th of July, which was meant to be yourself, Jason, doing an introduction to hydrogen line and tour of your telescope. Is after tonight? Is that? Do you still think? I mean, it'd be great if you have got something to speak about. But
I'll still plan to do that, and it'll be a little more formalized than what I did today. Like I'll go through the beginner's guide to the hydrogen line, and then like a short presentation on more of the details of the design and construction of my dish. So.
Actually, Andrew,
yes?
If you have a couple of minutes, I'd like to maybe, since Jason's here, I'd kind of like to show him something.
Okay.
And that, from what we discussed the other day regarding M31, I don't know if you think that might be interesting to him.
Yeah, sure. But I mean, in case anybody wants to shoot off, I will just say that the next meeting then will be the first Monday in July. Jason's going to be speaking to us, which will be brilliant. So next week we've got, I think it's the GNU radio for anybody that would like to take part in that. Bear in mind that will also be or is back on Teams. Everything this month is back on Teams now. If you haven't got the Microsoft Teams meeting for the link for that, then please do drop me an email and I'll let you know. The other thing just to bear in mind in case you didn't pick it up, because I know there's some confusion in that Rich sent out a set of links after I'd already sent out a correction, which is the 22nd of June, Monday the 22nd of June for the VLF meeting is no longer on the 22nd, that's on the 20th, Saturday the 20th. So if you haven't got, if you're aware of that, please do correct that on your diaries. Okay, over to yourself then, Adrian. Oh,
okay. I just thought maybe Jason might be interested in seeing kind of the stuff we were talking about M31 actually the other day, so what we tried to do actually was Andrew and I were trying to be exorbitant and just kind of burn some of the credits on the 20-meter Green Bank radio telescope. And so what we did is we set up some map scanning of several objects that we were trying to look at. And so let me see if I can. So
sorry, Adrian. Can I just rephrase that? We weren't trying to be exorbitant. We had a carefully thought out exercise in deciding what we were going to do with the 20-meter, and we carefully considered how we could most efficiently use the credits to get maximum output, and then we blew it all out of scan.
Okay, I was just trying to cover my fanny. Let me see if I can find this, because I'm not too adept at the sharing here on Teams. It kind of works a little bit different. So, gosh, I don't know. Let's see.
Can I say all this was Jason's fault? Because whenever I do it with Jason, he's so careful that we only spend just the right number of credits. And then we also noticed that Dimitri produces amazing results depending on about one credit. So.
Well, let's see. Let me see if I can really quickly find this here. Let's see. That's not going to be it. Give me a second here to kind of navigate through where this stuff is. Okay. Yes. Okay. This is it right here. Are you seeing a screen here with some of these thumbnails?
Yeah. Yep.
Okay. Great. Okay. Fantastic. So Jason, we tried an attempt of using the 20-meter radio telescope to do a map scan of M31. Mm-hmm. And so the parameters that we set are, so this is kind of the output from the 20-meter, which is horrendous. You can see the 1420 spike there, and then this kind of a blob on the side. And this is the kind of the raster scanner.
I see no spike.
Yeah,
I see a list of files.
Yeah, we're still seeing
a list of files. Oh, okay.
We're still seeing the opening screen.
Okay, so that's not the right thing then. How can I get this to show up?
If you stop sharing and then reshare and then select your whole screen instead of a particular window, it should show you what you're seeing on your screen in total.
Okay, let's see. I have to get out of the Teams. Oh my gosh, this is becoming a. Where in the world can I find? Okay, here's Teams, and so oh, that's to join. That's not even it. Oh gosh. So it's still showing the screen with the thumbnails.
Yeah, it's showing the screen with all of the observations in a list.
Oh, so this is the observations from the Skynet.
Yeah.
Okay, well, that's definitely not what I wanted to show. Did that go away now?
Yeah, that went away. Yeah.
Okay.
Try sharing again and see if it'll let you select your entire screen instead of just a single window.
Okay, so unshare.
Do you remember we did this the other day, Adrian? The difference between Windows and screen.
I know it's looking different now from so unshare.
See, you press share, and then on the left-hand side it says window, and the right-hand side it says right-hand side it says window, and the left-hand side it says screen. So if you're happy to just share whatever's on your screen, then click on screen.
Okay, well, I'm putting Windows on now, and let's see.
But if you click Windows, then it'll be whatever window you select. And the problem is, when you change window, it stays on the old window. That's the problem.
Yeah, okay. So you want to share your screen instead of sharing the window.
Well,
I think you are doing fine because you've. Oh, hang on, I don't know. You just.
Okay, I stopped sharing. And so you say share.
Press share, and then when it comes up, under presenter mode it says screen just above Microsoft Whiteboard.
Okay,
select
so I'm
screen.
So in doing that, and then share.
Yep.
There we are.
There you go. Yep, that's it.
You got me.
Okay, so. All right. So
now we see what you see.
Okay, fantastic. Okay, so let me see if I can now get to where I wanted to go. Let's see. Since I don't have this in this presentation mode or anything. Okay. So am I going down the list here of some of my folders?
Yes, you are. You can see that.
Yep.
Okay. All right. So that's going to get us there. Okay.
No, it's working very well now.
Fantastic. Okay, let me see now. And that's the folder where it's at. Okay, open that. And then, okay, so now hopefully this will show the output from the 20-meter radio telescope. Is that correct now?
It does.
Yeah.
Okay, so now this is what I was referring to. Okay, so this is the output from the attempt of the raster scan. And so you can see the spectra now, hopefully, and then that shows the, the spike there at 1420 from the, and this is kind of a raster scan, so it's using it's not narrowband, so there's not a lot of resolution there. And then, of course, the raster plots are kind of these horrendous blobs of sort of rainbow on the panels. And on the left, you see kind of the raster scan that we attempted. So we were trying to be conservative and trying not to, again, exceed too many of the credits that would be involved in mapping a figure. And so what I then said, well, gosh, that's horrible. Have other people had any better luck at doing the same thing? So going down the list of some of the other observations that have been made on the 20-meter radio telescope, I ran across this one. And I'm not sure if this is coming through, but this is again for M31. And I think you can maybe see the outline of it in some of those top panels.
Oh, yeah, definitely.
But now look at the raster scans that this individual used. And it's actually not an individual. I believe this is a class block that the Skynet has for, I believe it's University of North Carolina that has the intro-astronomy course, and so they're kind of unlimited in the number of credits that they can use.
Mm-hmm.
And so I estimate that with the number of raster scans and the time needed to do this particular observation, they probably went through like something like 1,400 credits.
Oh, wow.
I think the Sarah block usually gets like maybe 2,000 or 3,000, so this will be kind of exorbitant. But it's a nice, beautiful picture of M31, and I think maybe below it you might even see one of the other satellite galaxies.
Yeah, like M110 or whatever.
Yeah, I think you can maybe see some of those blobs. So anyway, this is what the 20-meter telescope, exceeding by 20-fold. Jason, your 1.5 meter telescope can do in order to image the M31. And so I just kind of wanted to show our failure, I guess. And I don't know.
Actually, go back to that one. Go back to that first one.
Yeah,
you can actually see the structure. That
Yeah.
diagonal structure is there.
A little bit, yeah. But again, the integration time was too short. The resolution was too short on the raster scans, and so
Yeah,
it's
the main problem is that even though it's not in the plane of the Milky Way, the size of the signal from the Milky Way, even out of the plane, is so much larger than the size of the hydrogen signal from M31 that you're basically getting RFI from our own galaxy.
exactly, yeah. And
so,
you're not selecting for even the velocity of Andromeda here that would maybe pull out some of the signal from the Milky Way. So
actually, that's actually pretty easy to correct for. The fortunate thing about M31 and M33 both is that they're significantly blue shifted because they're moving towards it at a fairly high speed.
Precisely.
And so for instance, when I'm doing drift scans for M31, I'm setting my center frequency at 1421.9.
Yes, yeah, that would.
And I think if you repeated this raster scan, but set your center frequency at like 1421.9 or something like that, you might actually see it might actually bring it out more because you would be above where the most of the Milky Way signal is.
Yeah, and that might work. I'm not sure because the bandwidth with raster scanning is quite broad. But let me show you, for example, and I think this is one of the students that this must have been an assignment. And so this is their attempt, even with that many raster scans, and you can see how much poorer the resolution and everything else was. And it's probably because they changed integration times and whatnot on the setup. So
is there an option in the raster scanning to use a single point observation somewhere at the off to the corner of the scan as a reference, and then
the sort of the back end processing is pretty much baked into the setting when you use
because I think that would greatly
it would, but you have no control over that directly. You'd have to essentially pull out the FITS file for the whole observation and then do your own processing on it in order to be able to do that kind of thing.
Which essentially what Andrew and I did a year ago is we, instead of doing a raster scan, we did a bunch of points where we did on-off, and we captured the spectra.
Yeah.
And then we sucked all those spectra. It was really labor intensive, but we sucked all of those spectra into Excel, and I basically did a bunch of post-processing, and we created 2 grids, actually. We created an intensity grid, and actually we did 4. We did an average and peak intensity grid, and we did an average and peak Doppler velocity grid. And the velocity grid was really cool because you could actually see, we color coded it red for the most extreme red shift and blue for the most extreme blue shift, and then we made it red yellow blue gradient over those values. And so it gave us basically a really pretty illustration of the Doppler velocity, and you could see the motion,
I recall that presentation you guys did. That was really excellent. That was really,
But it took a lot of manual labor to do that, though.
I can only imagine. Yeah, I can only imagine doing all that by manual. But yeah, unfortunately, the sort of the values for all the integration and so forth on the now there's some settings with the GBT portal there that I'm not entirely sure how to use, and whether there might be some other alternative means of processing it, but they're sort of default processing is pretty much baked in for any of the settings that you have, whether it's on, off, or track, or DAISY, or this for mapping, and they're pretty much the default values that you get whenever you just kind of push run. And Jason, I don't know, you seem to have a little bit of contact with the Green Band people. There, actually, Andrew and I had one more observation that's been sitting there now for more than almost like a week and a half or two, and it has not been processed. And I do realize, because you can go. There's a listing. Actually, there's a chronological listing of all the observations that are being made on the Green Bank, and you can look through that list. And I know that there's observations that have been done way after we've set up that.
There's got to be something. Yeah, there's got to be something up with that. Yeah,
I think people get maybe priority over like our user sort of subscription.
Well, in some cases, but I don't think that's the issue. Dimitri and I have both experienced problems with a particular observation where it just won't run. It just doesn't run, and sometimes it's a software glitch or some kind of issue where where you just basically sometimes they can do stuff on their end to get it to go ahead and run, and sometimes you just have to delete it and run a new one. The good thing is you don't get charged for it if it doesn't run. So. Oh yeah,
and we've had to cancel some observations. I know you get credit on that, and until they run. Yeah.
If you send me an email with the details of the one that's not running properly, tomorrow when I go back into the office, I'll email my contact at Greenbank and let her know what's going on and see if she can figure out a solution to it.
Okay, well, and after you contact them about the X-band to switch to the receiver, boy, I mean, like the next day they took it off, and that was kind of sad because I had already a couple of other observations that I would have liked to have done of just a continuum, which is fantastic at X-band, and it sure will be nice if they could sort of schedule in putting it in at some periods and fixing some of those problems that both Dimitri and I had observed on their portal. But in any case, I don't know, Andrew. Did you take my sharing off? I was trying to find it.
So sorry, I removed it. You can put it back on if you want.
No. I was trying to find it. So thank you very much. I appreciate it. I wanted to.
My contact at Greenbank was saying that I think it's really a funding issue where they have funding, they have a steady stream of funding to support the infrastructure around the L-band receiver because of all the projects that are on it. But the X-band was kind of like, well, we can put it on there, but you get what you get, because they don't have specific funding to support that,
I see. Well, that would be an issue. It sure would be nice though if they could maybe put that on for some periods of time, maybe like maybe once every couple of months or something for a week or something like that would be fantastic. But if it's a funding issue, I can easily see how that could be a real problem in the especially in the environment.
She did indicate that they would like to do that, and so they may be pursuing some funding avenues to add the X-band capability and expand that. So they definitely have an interest in doing that. It's just a matter of the logistics of it. So.
Oh gosh, the beam size that you get at X-band and of course the different frequency range would be fantastic compared to L. But anyway, I just thought you might find interesting there that M31 observation that has that capability with with a 20 meter and actually get a picture, which is sort of a qualitative view. But yeah, Andrew and I have been working on some stuff where actually a qualitative picture can give you some very somewhat surprising results that wouldn't necessarily be available if you were just looking at a single frequency. And I might show that at some other time, but we're running out of time today.
Well, that was pretty cool that even in that first one that you showed, you couldn't see anything very clearly, but you could definitely see the diagonal structure.
A little bit of it,
there.
yeah.
You know, you could see, you could tell that you were seeing something.
Yeah, well, it was an effort. there are better targets for the time available for us to be sort of at least reasonable with the amount of credits that mapping does use from the SARA allotment. But
which
anyway.
I kind of got the impression that if we start using more, Sarah might be willing to buy more. You know, I mean, I don't necessarily think there's some kind of hard limit, you know, because it's our money, you know, our dues that are paying for it. So I don't think if we really start using more, they might just replenish them more often. You know,
well, that could very well be. I know there's not necessarily a limit on number of credits that can issue, and of course this might be a slightly different situation. But a number of years back, I was able to attend the single dish school that Green Band puts on every year, and for that class, they had something like 30 or 40,000 credits allotted to it. Of course, there were quite a number of people there, and it was shared among different groups. But there was a huge block of that. I still actually have a few credits left on that account that were assigned to me. So. Kind of keep them in my back pocket there because I want to have a real special observation that I want to run and not burn necessarily the Sarah credits. But if Sarah bought more, and I think more people should really. That's Andrew and I were speaking about that. Sarah stresses, please use the 20 meter, and not that many people use it. People just kind of.
Well, I like the fact that I think the last period of credits that they purchased was the first time we ever used them all up, and it was between myself, Andrew, and Dimitri, I think mostly, that used up all those credits, and it was kind of our goal. Our goal was we want to use those credits up so they'll buy more.
I burnt up a few of those. I mean, I actually did a couple of scans that probably ran about 400 or 500 points. So I took a little chunk out of it myself, and actually these observations took a pretty good sized chunk out of the current. But I figured, well, it's been sitting there for a while. It's time to start purchase some more. So
well, I figure use them until they tell you not to, right?
Exactly. Yeah, and I'd love to do more mapping scanning for some other objects.
Oh, my bad.
Yeah, sorry. You said use it. You didn't say how much.
Well, I have a proposal. That we should, between us, do a scanning exercise that starts at NGC 7000, progresses through the entire Cygnus region, down to the Cygnus loop, and perhaps out the back of Cygnus as well.
Just do the whole new general catalog. Why stop at any individual number?
We could do an entire Sky L-band catalog scanning exercise.
Oh God. Anyway,
it is funny though. One of the things I remember Andrew and I doing with our, labor-intensive Doppler mapping exercise, we I think it was a few months after the conference when we did we added on some stuff, but we did, what was it, the M81, M82, and whatever that third one is, and we couldn't resolve the individual galaxies. They were too small, but there's a large structure between two of them that's like a big long plume, and we were able to just barely resolve that with the 20 meter. You remember that, Andrew?
Yeah.
And I still have that on my wall. I still have hard copies of that pasted up on my file cabinet in my office. So,
well, I won't show that today, but I have a scan we have a scan that we're actually able to resolve the galactic plane, the hydrogen background galactic plane.
Oh wow, yeah.
So it's another observation that we did that's actually for a supernova remnant called W44, and it's right in the plane of the galaxy, and in the background you can have a diagonal stripe that's because it sits right in the galactic plane, and you can see the galactic plane kind of coming across the scan. So that was kind of cool, unexpected, but anyway, we'll talk about that some other time.
Which actually reminds me too. I was watching some deep sky YouTube videos. It's the channel from one of Brady Heron's channels out of YouTube channels out of the University of Nottingham, and it's the astronomy one, and they have basically videos about a bunch of the different Messier objects and some of the NGC catalog objects, and one of the ones they did was this one that Edward found that was kind of halfway between M33 and M101 in signal strength, and it was one that wasn't on the other catalogs that I'd been using as my reference guide, and I was like, how did I miss that? And he actually explained why that was. He said this it's not in any of the older catalogs like Messier's catalog or the NGC catalog. It's IC342, and it's relatively bright and large angular size, but the reason why it gets missed is because it's so close to the galactic plane that it gets buried in the galactic stuff that's in the foreground. And so I thought that was interesting.
Yep.
But in the hydrogen, because it's somewhat redshifted, it's bumping right up against the Milky Way signal, but there is a portion of it that just peeks out from the redshifted side, and so you can see kind of most of it, like 3/4 of it, coming out from the hydrogen, the galactic hydrogen, and it's about twice as large as M101, or about 40% as large as the signal from M33. So it's definitely in that middle ground, and so that's definitely the next one I want to go after with my small dish. But yeah, that was interesting. It was the reason why it got missed is because it was just in a bad place. It was in too busy of a neighborhood in the sky.
Well, especially when all those observations were done with optical astronomy. So
yeah, exactly.
Yeah, that really just blinds anything back there. Anyway, that's kind of interesting observation there.
Well, thank you very much, there, Adrian.
That's all I had to say, Andrew. So
yeah, no, sorry. Thanks very much, Adrian. That was, I think, that was a nice way to finish the meeting. So, what I'm going to do now is I'm going to bring this meeting to an end and stop the recording.